Hi students, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss some of the important formulas of the electronics in a very detailed manner. And if you like the comment of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notifications comes through. While if any improvements are needed in our video lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So in this lecture, we are going to learn some of the important formulas of electronics. Here, this is called as the rectifier module. In the rectifier module, we are going to study the two basic things, which are the single phase and the three phase. So in the rectifier module, we are going to study the two basic things, which are the single phase and the three phase. So in the single phase, we are going to study the half wave rectifier module and the full wave rectifier module. And in the half wave, we are going to study the uncontrolled and also controlled. In the uncontrolled, we are going to study the loads, which are the R load, L load, RL load, RL with the freewheeling diode, and also RE load. All these loads we are going to study in the uncontrolled fashion. Yes, we are going to keep the diode, and then for the single phase source, we are going to keep the diode, and with the help of all these variations of the loads, what are the current, what are the voltages, all the things we are going to analyze for each and every particular load. Similarly, for the controlled, means we are going to keep the thyristor. Then with the help of thyristor is the controlled. So therefore now here we are going to vary the loads of R, L, RL and RL freewheeling diode and RE load. With all these loads, we are going to see what is the variation of each and every parameter in a circuit we are going to study. And similarly, in the full wave configuration, we are going to study the uncontrolled, means only diode is going to present, and in the controlled means only thyristors are going to get present, and in the semi-controlled, we are going to keep both the diode and also thyristor. And also here we are going to study the symmetrical, asymmetrical and full converter plus freewheeling diode. See, for all the variations of load, R load, RL load, RE load and RL load. So for these different types of loads, for all the configurations, we are going to study in a very each and every minute, for each and everything in a detailed manner. And also in the three phase, we are going to study the half wave and also full wave. In the half wave, we are going to study the uncontrolled and also controlled, whereas in full wave, we are going to study only the control. So basically in this rectifier module, we are going to study the single phase and three phase. In the single phase, we are going to study the half wave and full wave. In the half wave, we are going to study the uncontrolled and controlled. In the uncontrolled means we are going to keep only the diode. So now we are going to vary the load as R load, L load, RL with the freewheeling diode and RE load. And similarly in the control, here means control means we are going to keep the thyristor. Then we are going to vary the load as R load, L load, RL with freewheeling diode and RE load. And for full wave, we are going to study the uncontrolled means only we are going to keep the diode, and whereas controlled means we are going to keep the only thyristors, whereas semi-controlled means we are going to keep both the diode and also thyristor. And also we are going to study the symmetrical, asymmetrical and full converter plus freewheeling diode in this semi-controlled section. And then for each and everything we are going to vary for R load, RL load, RE load and RLE load. For all this load, we are going to see what is the variations of the current, voltage and each and everything we are going to study. So this everything is under the category of the single phase. So now for the three phase, we are going to study the half wave and full wave. For half wave, we are going to study the uncontrolled and controlled, whereas for full wave, we are going to only study the control. So each and everything we are going to study in a detailed manner in this rectifier module. So let's get started for each and everything. So now phase control rectifier. Phase control rectifier is we are going to study the phase control rectifiers into two fashions. Same thing as you have studied previously, single phase and three phase. Single phase means we are going to study the half wave rectifier and full wave rectifier. And in the full wave rectifier, we are going to study the split phase midpoint and also bridge type rectifier. Whereas in the bridge wave rectifier, we are going to study the full converter and the semi-converter. Full converter means we are going to use all the thyristors, whereas semi-converters means we are going to use the combination of thyristors and diodes. Similarly, in the three-phase also we are going to study in the same fashion as the previous one, half wave rectifier and the full wave rectifier. In the full wave rectifier, we are going to study the split phase midpoint and the bridge type rectifier. And the bridge type rectifier, we are going to study the full converter and the semi-converter. Same as so whatever the things we are going to study for the single phase, same concepts we are going to study for even three phase also. So phase control rectifier, we are going to study the two important things, which are the single phase supply and three phase supply. For single phase supply, we are going to study the half wave rectifier and full wave rectifier. In the full wave rectifier, we are going to study the split phase means midpoint and also bridge type rectifier. And in the bridge type rectifier, we are going to study the full converter and the semi converter. Similarly, in the three phase supply also, we are going to study the half wave rectifier and the full wave rectifier. In the full wave rectifier, we are going to study the split phase midpoint and also bridge type rectifier. In the bridge type rectifier, we are going to study the full converter and the semi converter. So whatever the things that we are going to study for the single phase, same concepts we are going to study for even three phase also. So now we are going to study the half wave uncontrolled rectifier. Half wave uncontrolled rectifier. Half wave uncontrolled rectifier. Half wave means only in a half wave means basically we can say that in a one time period only one pulse is going to get present, and also uncontrolled means we are using the diode here. So and it is a rectifier means converting AC to DC. That is the meaning of this definition. Half wave uncontrolled rectifier means only one pulse in a given time period, and it is a diode we are going to use, and rectifier means converting AC to DC. So here you can take this is a single phase supply. Supply source is Vs of t and it is going to deliver a current of Is of t. And here we are going to keep a diode of plus minus Vd of t, ideal diode we are going to assume, and here we are going to keep a resistor R. The voltage across the resistor R is V of t and the current through the load is I naught of t. So you can see clearly this is the circuit diagram. When Vs of t greater than 0, when Vs of t is greater than 0, you can say that the diode is on. Whenever the diode is on, whatever the output voltage will be equal to input voltage. So output voltage is equal to input voltage, which is V naught of t is equal to Vs of t. Means the diode voltage is equal to 0 at that time. When Vs of t is less than 0, means diode is reverse bias. So diode is reverse bias means diode is off. So therefore we can say that the circuit is open. So therefore output voltage is equal to 0. So we can say that here similarly if the diode is on, the input current is equal to output current. Here the input current is equal to 0 and also output current is equal to 0 when the diode is off. So when the diode is on, output voltage is equal to input voltage and output current is equal to input current. When the diode is off, the output voltage is equal to 0 and the output current is also equal to 0 and the source current is also equal to 0 in this case. Now let us draw the graphs of this one. Let me assume the source voltage, let me assume it is a sinusoidal voltage having a peak value of Vm and minus Vm. So one time period is 2 pi, so half time period is pi. With respect to theta I am going to take here. And here from 0 to pi we can say that the supply voltage is greater than 0. As the supply voltage is greater than 0, the diode is on. So therefore whatever the output voltage has to be equal to the input voltage. So output voltage is going to follow the input voltage in this region. And I have already told you in this region the output current is equal to output voltage by resistor. So we have divided by R. So Vm by R. Let me assume this is the peak current. And also in this region the diode is on. In this region the diode is on. So therefore we can say that here as the diode is on, whatever the diode is on means the diode voltage is equal to 0 because we are going to assume it is an ideal diode. Whereas in pi to 2 pi the supply voltage is less than 0. Less than 0 means negative. So we can say that the diode is reverse bias. So diode is off. So therefore diode is open circuited. So output voltage is equal to 0. As the output voltage is equal to 0, so output current is also equal to 0. As the output current is equal to 0, source current is also equal to 0. So therefore I naught of t is equal to Is of t always, because there is no extra branch present. So we can say that I naught of t is equal to Is of t in this case. So this is the current we are going to get, source current and also load current. Whereas diode is reverse bias. Diode is reverse bias means if you apply the KVL, we are going to get plus Vs of t minus Vd of t minus V naught of t is equal to 0. As V naught of t is equal to 0, we can say that simply, which is Vd of t is equal to Vs of t. So Vd of t is equal to Vs of t simply indicates that the diode voltage is going to follow the source voltage in this region. As the source voltage is negative, so we can say the diode voltage is also negative. So this is the voltage we are going to get with a peak value of minus Vm. So peak inverse voltage means the maximum reverse voltage experienced by this diode is Vm. So peak inverse voltage of this diode is Vm. So this much amount of reverse bias we are going to get across. So we can see clearly in the output voltage there is only one pulse in a given time period. So we can say this is one pulse converter, means if the output voltage is going to have only one pulse, then we can say this is one pulse converter. So let me do the analysis of this circuit. As I already told you, there is no extra branch. So because of that, whatever the source current should be always equal to load current. And if both are equal means their average values are equal and also their RMS values are also equal because both are same. So the source current RMS value is equal to load current RMS value, and also source current average value is equal to load current average value also. So now I want to find what is the average value of the output voltage. So average value of the output voltage is equal to 1 by time period into integration of time period V naught of t into dt. So therefore we can say now we are going to do in terms of theta. So 1 by 2 pi integration of 0 to 2 pi V of t is V of t into d theta. But here we can say that simply this pulse is present only from 0 to pi but not from pi to 2 pi. But the actual formula is 1 by 2 pi integration of 0 to 2 pi. Here the supply voltage Vs of t into d theta. But here Vs of t is nothing but Vm sin theta, and from pi to 2 pi the pulse is 0. So pulse is present only from 0 to pi. So 0 to pi Vm sin theta into d theta. So if you solve this one, we are going to get Vm by pi. So Vm by pi is the average value of the output voltage. So Vm by pi is the average value of the output voltage. So if you want to know what is the average value of the output current, so V naught average is equal to I naught average into R. So therefore I naught average is equal to V naught average by R. So V naught average value just now we have known, which is Vm by pi. So if you substitute here, we are going to get Vm by pi into R. As I have already told you, Vm by R is called as the peak value of the current, which is Im. So Im by pi. So we can say that I naught average is equal to Im by pi, where Im is equal to Vm by R. So this is the way we are going to get. And also I naught average is equal to V naught average by R. So these are the different formulas we are going to get. And if you want to know what is the RMS value of the output current, which is under root over 1 by 2 pi integration of 0 to 2 pi V of t whole square into d theta. But from pi to 2 pi the signal is 0. So integration is going to come for only 0 to pi. So now is equal to, so if you solve this one, we are going to get Vm by 2. So Vm by 2 is the RMS value of the output voltage. And if you want to know what is the RMS value of the output current, which is simply we can say that V naught RMS by R. So but V naught RMS is nothing but here simply V naught RMS just now we have known, which is Vm by 2. So Vm by 2 if you substitute, we are going to get in this expression. Or if you go for current, we are going to get Im by 2 also, where Im is called as a Vm by R. So Vm by R, same thing. So no matter whatever the expression, you are going to get the same result. So I naught RMS is equal to Im by 2 and V naught RMS is equal to Vm by 2. And output power is equal to means the amount of average power absorbed by the load, which is V naught RMS square by R is equal to I naught RMS square into R. Because there is only resistor, so resistor is going to consume active power, which is I naught RMS square into R or V naught RMS square by R. You can go for any of these two formulas to get the average power absorbed by this load resistor. And we are going to assume that there are no losses in the ideal diode. So therefore whatever the input power is always equal to output power. input power expression is Vs RMS into Is RMS into cos phi is equal to I naught RMS square into R. This is called as the input power and this is called as the output power. This is called as the input average power and this is the output average power. They should be equal because the losses are 0. So Vs RMS into Is RMS into cos phi is equal to I naught RMS square into R. So now here I have already told you the input current is equal to output current. So the source current RMS value is equal to load current RMS value. So therefore one term is going to get cancelled. Then finally we are going to get cos phi is equal to I naught RMS into R by Vs RMS. I naught RMS into R is called as the V naught RMS by Vs RMS and V naught RMS is Vm by 2 whereas Vs RMS is Vm by root 2. So if you solve this one we are going to get 1 by root 2. So 1 by root 2 is 0.707. So the power factor, the input power factor is equal to 0.707. The input power factor of the circuit is 0.707. So this is the input power factor which is 0.707. If you want to know what is the conduction angle of diode, conduction angle of diode means for how much angle the diode was conducting, for how much angle the diode was conducting from 0 to pi, from 0 to pi we can say that the diode is conducting, from pi to 2 pi the diode is off. So only for a region of 0 to pi or we can say 0 to 180 degree the diode was conducting. So the conduction angle of diode is equal to 180 degree. Extension angle is represented by a symbol beta. Extension angle is represented by a symbol beta, means up to what angle I naught of t exists. You can say that extension angle means beta, up to what angle I naught of t exists. See, this indicates that conduction angle means the representation is beta. This beta, it indicates that up to what angle I naught of t exists, means up to what angle the load current is going to get exits. That is the meaning we need to figure out. So only up to 180 degree, at theta is equal to 180 degree, the I naught current has become 0. So however it is a 0 in a one cycle. So therefore we can say that the extension angle, or we can say that simply at what angle, up to what angle the load current is going to get exits, it is equal to beta is equal to 180 degree. So only up to 180 degree the current is going to get present. So extension angle is equal to 180 degree and peak inverse of diode is equal to Vm. Just now I already told you this much amount of reverse peak voltage should be experienced by diode to withstand that one. So we have to always design a diode of peak inverse value which is greater than Vm, or we can say that peak inverse voltage of the diode is equal to Vm. Circuit turn of time means Tc is equal to, so circuit turn of time Tc is equal to pi by omega, means up to how much amount of time the diode is reverse bias, for how much amount of time the diode was reverse bias. That is the meaning of the circuit turn of time, is for how much amount of time we are going to apply a reverse voltage across the diode, which is from pi to 2 pi. From pi to 2 pi we are going to apply the reverse voltage. So what is the angle between them? 2 pi minus pi is pi, but we want that time, so therefore pi by omega we are going to get the time. So circuit turn of time is equal to pi by omega seconds. This much amount of time we are going to give a reverse voltage across the diode. So these are the analysis of this circuit. So now we are going to study the another circuit. So another circuit which is here, this is a supply voltage, single phase supply voltage, and here we are going to keep the load, here we are going to keep the diode, and here now we have replaced R load by L load. See, only thing from the previous circuit is just we have replaced the R load by L load and remaining everything is same. So we can say that this is also single phase, means single phase converter. So therefore we can say that here single phase uncontrolled converter or rectifier. So this is Vs of t, here Is of t, I naught of t, and this is V naught of t. This is the inductor is L and this is the Vd of t. So now what is going to happen? Let me assume the diode is on. When diode is on, then we can say that as I am assuming the diode is an ideal diode, so whatever the supply voltage is equal to load voltage. Let me assume the supply voltage Vs of t is equal to Vm sin omega t. So whatever the load voltage should be equal to supply voltage. But the voltage expression of inductor and current is the voltage and current relationship across the inductor, which is V naught of t is equal to L into d I naught of t by dt. But I have already told you when the diode is on, the load voltage is equal to source voltage. So Vs of t is equal to L into d I naught of t by dt, which is Vm sin omega t is equal to L into d I naught of t by dt. So now here I want this one. So d I naught of t by dt is equal to, I am taking the L to the down port, we are going to get Vm by L into sin omega t. So now I take the dt to the right side, I am going to get like this. So now I am doing the integration. Let me assume the initial current in the diode is 0. I am assuming that the initial current in the inductor is 0 from 0 to I naught of t, and the time is changing from 0 to t. So I am assuming that at time t is equal to 0, the current in the inductor is 0. I am going to assume like that. At time t is equal to 0, the current in the inductor, I am assuming that it is 0. So by this integration from 0 to I naught of t and from 0 to t, if we do the integration, finally we are going to get I naught of t is equal to Vm by omega L into 1 minus cos omega t. So if we do integration and if you substitute the units, finally we are going to get, which is I naught of t is equal to Vm by omega L into 1 minus cos omega t. Means at a time of t, this is the value of current which is going to present in this circuit. So I naught of t is equal to Vm by omega L into 1 minus cos omega t. Means at a point of time t, we are going to get this much amount of current is going to present in this circuit. So I naught of t is equal to Vm by omega L into 1 minus cos omega t. So this is the expression of the current in this circuit. So I naught of t is equal to Vm by omega L into 1 minus cos omega t. So for 0 to pi, we can see clearly that V naught is greater than 0 and I naught is greater than 0. So for 0 to pi, V naught is greater than 0 and I naught is greater than 0. So we can say that if we do the product of these two things, we are going to get P naught greater than 0. Means simply power is transferred from source to load, means the power is the load is going to absorb the power. This power is going to come from source. So we can say that from 0 to pi, V naught is greater than 0 and I naught is greater than 0. So if we do the product of these two things, we are going to get P naught greater than 0. It indicates that the load is absorbing the power, means, or simply the power is coming from source to load. Whereas from pi to 2 pi, V naught is less than 0 but I naught is still greater than 0. Whereas if the product of these two things, P naught is less than 0, it indicates that power is transferring from load to source. Means from pi to 2 pi, we can say that V naught is less than 0 and I naught is greater than 0. So if the product of these two things, we are going to get P naught less than 0. It indicates that the load is delivering power to the source. The load is delivering power to the source, or power is transferred from load to source. That is the meaning of this one. So from 0 to pi, the load is absorbing the power from source, and from pi to 2 pi, the load is delivering the power to the source. So this is the diagram we are going to get. See, this is a source voltage is equal to Vm into sin omega t. So if you draw this, we are going to get in this shape with respect to theta, pi and 2 pi. So with the peak value of Vm and minus Vm. I have already told you for 0 to pi. So therefore here always V naught of t is equal to Vs of t. Always V naught of t is equal to Vs of t. So we are going to get in this manner, means the load voltage is equal to source voltage. The load voltage is equal to source voltage. And I have already told you the load current. The load current I naught of t expression is Vm by omega L into 1 minus cos omega t. So if you substitute omega t is equal to 0, we are going to get current is equal to 0. If you substitute omega t is equal to pi in this expression of current, we are going to get 2 Vm by omega L we are going to get. And if you substitute omega t is equal to 2 pi, we are going to get current is equal to 0 in that expression. So this is the graph we are going to get. So you can see clearly from 0 to 2 pi, the current is always positive. The current is always positive indicates that the diode is always on. The diode is always on. From 0 to 2 pi, the diode is always on. So whereas as the diode is always on, we can say that it is the ideal diode. So voltage drop across it is 0. So therefore from 0 to 2 pi, the voltage drop across the diode is always equal to 0. So this is the thing that you need to analyze. So you can see clearly from 0 to 2, from 0 to pi, V naught is greater than 0 and I naught is greater than 0. So their product power is also greater than 0. It indicates that the power is transferring from source to load. Whereas from pi to 2 pi, the voltage, output voltage is less than 0, whereas current is greater than 0. So if the product of these two things, the power is less than 0, it indicates that the power is transferring from load to source. That is the meaning of this one. So diode is always on from 0 to 2 pi. So because of that, the voltage drop across the diode is equal to 0 for all the time. Due to the analysis of this circuit, as I already told you, here output voltage average value, because it is a pure sinusoidal waveform, so overall output voltage average value is equal to 0. So always listen carefully, always the average output voltage of an inductor is always equal to 0 and the average value of the capacitor current is always equal to 0. Listen carefully, the average value of the voltage across the inductor is always equal to 0 and also the average value of the capacitor current is always equal to 0, and also here I naught average is equal to. So if see this is the expression of the current, which is V naught of t is equal to Vm by omega L into 1 minus cos omega t. So if you want to know what is the average value of the output current, then we can say clearly this part is going to become 0 because cos term is a sinusoidal waveform, its value is equal to 0. So only constant part we are going to get, which is Vm by omega L. So Vm by omega L is the average value of the output current, and if you want to know what is the maximum value of the output current, maximum value is going to occur at omega t is equal to pi. At omega t is equal to pi, cos pi is equal to, simply we are going to get minus 1. So minus to minus is plus 1 plus 1 is 2. So finally we are going to get 2 Vm by omega L. The maximum value of the output current is going to occur at theta is equal to pi. Its value is equal to 2 Vm by omega L. And I have already told you there is no extra branch, so therefore the output current is always equal to source current. So always its average values are equal, RMS values are also always equal. So RMS value of the output voltage is equal to Vm by root 2, and the conduction angle of the diode is equal to, which is gamma d, is called as the conduction angle of the diode, means the diode is always conducting for 0 to 2 pi. So we can say that its time period is 2 pi. So for all the time it is going to get conduct, and the extension angle is equal to beta. It indicates that up to what angle the current in the node is going to present. It is up to 2 pi it is going to present. So therefore we can say this is 2 pi. And here the diode is always conducting, so there is no reverse voltage. As there is no reverse voltage across the diode, so circuit turn off time is also equal to 0, because circuit turn off time indicates that up to how much time you are going to keep a reverse bias voltage across a diode or any thyristor or any switching device. So it is here 0 in this case. So this is some of the important analysis of this circuit. So now we are going to study the RL load. So in the first case we have studied the R load, then L load. Now we are going to study the combination of the R and L load. Then we have to see what is the measure of the current and voltage. And the source voltage is now Vs of t is equal to Vm sin omega t, and this is the load voltage, which is plus minus V naught of t. It is a RL load, and the load current is I naught of t, and the source current is Is of t. And this is the diode, ideal diode we are going to assume, and the diode voltage is plus or minus Vd of t. So now we are going to study the waveforms of each and everything. So now, as the source voltage is a pure sinusoidal waveform, so we are going to get in this format from 0 to pi and pi to 2 pi. So the peak value of plus Vm and minus Vm. As now the output voltage will be, see, for output voltage will be now, in the first case only from 0 to 2 pi, the diode was conducting. In the previous case from 0 to 2 pi, the diode was conducting. So now the diode will conduct in between the range of pi to 2 pi. So we can say that, let me assume up to angle beta, the diode was conducting. So therefore we can say, as the diode is conducting up to beta, So the output voltage is equal to source voltage. See, then output voltage is going to follow the source voltage up to angle beta because the diode was on. Because of that, the current is going to become like this, means the current is going to get increase up to certain angle, and after that it is going to decay and is going to finally become 0 at angle beta, and up to beta the diode was on, so therefore its voltage will be equal to 0 because the diode is on. We are going to assume the diode is a ideal diode, so up to angle beta the diode was on, so its voltage is 0. But after that the diode is going to become off. After that the diode is going to become off, so therefore when the diode is off, then we can say that the load voltage is equal to 0. So therefore the load voltage is equal to 0. So it is going to become abrupt change. Suddenly it goes from some non-zero value to 0 value we are going to get from beta to 2 pi, and the current is going to become 0 from beta to 2 pi. So therefore, see, the current in an inductor doesn't change instantaneously, whereas the voltage across the inductor can change instantaneously. So that is the reason here current is going to become 0 from beta to 2 pi, because as the diode is open, definitely the current should be equal to 0. And as the diode is open, we can say that simply whatever the source voltage should be equal to the diode voltage. So therefore now the diode is going to follow the voltage across the source. Whatever the source voltage in this region from beta to 2 pi, same will be across the diode also from beta to 2 pi. So with a peak value of minus Vm, or you can say the peak inverse voltage of the diode is equal to Vm. So this is the thing we are going to get. So we have assumed that the diode is going to off between in this region. So therefore the current is 0 from beta to 2 pi. So this is called as a discontinuous mode. Means here the current is going to have a 0 value in this period. So this is called as a discontinuous mode. Suppose if the current is non-zero, or over the total region, then we say it is called as a continuous mode. Whereas in this region the current is 0, so we call this as a discontinuous mode of operation. And I have already told you there is no extra branch, so therefore whatever the source current is equal to the load current. So now we are going to analyze the circuit. I have already told you from 0 to pi. From 0 to pi, here the output voltage is greater than 0. The output voltage is greater than 0, and also the output current is greater than 0. So therefore if you do the product of these two things, we are going to get P0 is greater than 0. So it indicates that the source is delivering power to load, or simply the load is absorbing the power from the source. Because from 0 to pi, the load is absorbing the power because V0 is greater than 0, I0 is greater than 0. So their product is also greater than 0. So it indicates that simply if the product is greater than 0, indicates that the power is greater than 0. It indicates that the load is absorbing the power from the source, or source is delivering power to the load. Whereas from pi to beta, the load voltage is less than 0 and the output current is greater than 0. Whereas if you do the product of these two things, the power is lesser than 0. It indicates that now the source is absorbing the power from load, or load is delivering power to the source. So from pi to beta, the load voltage is less than 0 and the load current is greater than 0. So therefore if you do the product of these two things, then output power is less than 0. It indicates that the power is transferring from load to source, or simply we can say that source is absorbing power from the load. So now I want to find what is the average value of the output voltage. So average value is equal to 1 by 2 pi integration of 0 to beta, because only from 0 to beta only the voltage was non-zero. So from beta to 2 pi it is equal to 0. That is the reason we are going to take only from 0 to beta Vm sin theta into d theta. So if you do a simplification of this one, we are going to get Vm by 2 pi into 1 minus cos beta. So Vm by 2 pi into 1 minus cos beta is the expression of the output voltage. Vm by 2 pi into 1 minus cos beta is the average value of the output voltage we are going to get in this expression. So Vm by 2 pi into 1 minus cos beta. And if you want to know what is the average value of the output current, because here V0 average is equal to I0 average into R plus the average value across the output voltage of the inductor. I've already told you the output voltage, or you can say the load voltage or the voltage across the inductor is equal to 0. So therefore simply we are going to get finally I naught average is equal to V naught average by R. And already V naught average value we know just now. Substitute here we are going to get finally Vm by 2 pi R into 1 minus cos beta. So this is the average value of the output current. So only thing that remember, which is V naught average is equal to I naught average into R plus the average value of the inductor voltage, the average value of the output voltage across the inductor. Average is equal to 0. So therefore V naught average is equal to I naught average into R. So therefore I naught average is equal to V naught average by R. So if you know the V naught average, we can easily find the I naught average value also. And now the conduction angle of the diode. The diode is conducting from 0 to beta. So therefore the difference is beta minus 0 is equal to beta. So this is the angle for which the diode is conducting. And I have already told you always the source current is equal to load current because there is no extra branch. So because of that, always source current is equal to load current means their average values are equal, their RMS values are also equal, which is IS RMS is equal to I naught average, and also IS average value is equal to I naught average value also. Whereas circuit turn of time. Circuit turn of time means the time up to which a reverse voltage, the time up to which the reverse voltage was occurred or appeared across the diode. Here I already told you from beta to 2 pi. From beta to 2 pi, the voltage across the diode is negative, means it is reverse bias. So now the angle is 2 pi minus beta, but we want the time, so therefore divide by omega. So this is the time for which the reverse voltage was occurring across the diode, or it is also called as the circuit turn of time, which is 2 pi minus beta by omega. And the peak inverse voltage of the diode is equal to Vm. Just now I already told you from the graph itself. So this is the peak inverse voltage of the diode should be. So now here there is another circuit. So now this new circuit we are going to analyze. See here, now in the previous case there is only RL load. So there is no extra freewheeling diode. But now we are going to keep the freewheeling diode across this RL load, and then we will analyze this circuit. So here this is diode D1 and this is diode D2. Everything is same, extra thing just we have kept this diode. This is called as a freewheeling diode and this is called as the main diode. So this is the source voltage Vs of t, source current Is of t. This is the load which is RL load. Here RL load means the output voltage is V naught of t. Here this is the output current or load current I naught of t, and this is the diode D2, which is called as a freewheeling diode. So D1 is called as the main diode and D2 is called as a freewheeling diode. Just we have kept this freewheeling diode across the RL load, and now we are going to analyze this new circuit. So now here this source voltage Vs of t is equal to Vm sin omega t. So this is the graph we are going to get. Its peak value is plus Vm and minus Vm. So now here in the previous case here from 0 to beta the diode was connecting, the diode main diode was connecting, but now here only from 0 to pi, from 0 to pi the diode D1 will be conducting. Only from 0 to pi the diode D1 is going to conduct. So therefore when the diode D1 is going to conduct, whatever the source voltage is equal to load voltage. So it is going to follow the source voltage. And from 0 to pi the current is going to get charged in this case. And similarly as the diode D1 was conducting, so its voltage is equal to 0. Whereas from pi to beta, or you can say in this reverse fashion, then in this reverse fashion what is going to happen, the diode D1 is going to get reverse bias, because as the Vs is less than 0, the diode D1 is going to get reverse bias. So as the diode D1 is reverse bias, then the diode D2, the freewheeling diode, is going to get forward bias. So therefore now what is going to happen, then the current is going to pass, the I naught current is going to pass only through the freewheeling diode. So therefore whatever the current is going to flow only through the freewheeling diode. So therefore we can say that here from pi to 2 pi, that as the diode D1 was open circuited, then as the D2, only D2 is going to get conducting. So therefore the output voltage is equal to 0. So therefore we can say this is the output voltage. And from pi to 2 pi the current is going to get decay in this manner. And from pi to 2 pi I have already told you the diode D1 was off, because only D2 is conducting in this region. So whatever the source voltage is equal to the load voltage. If you apply the KVL, we are going to get plus Vs of t minus Vd of t minus V naught of t is equal to 0. As V naught of t is equal to 0 in this case, so therefore we can say Vs of t is equal to Vd of t. So whatever the source voltage is equal to load voltage, whatever the source voltage is equal to the diode voltage in this case from pi to 2 pi. So it is going to blindly follow the source voltage. So from 0 to pi, D1 is going to conduct, and from pi to 2 pi, diode D2 is going to get conduct. So now you can see clearly the current is not discontinuous, always continuous, means there is no zero value. There is no zero value from pi to 2 pi. So we can say this is said to be a continuous mode of conduction. So with the help of freewheeling diode, we can make the continuous conduction mode is possible if you keep a freewheeling diode across a RL load. And also we are increasing the output average value also. In the previous case, there is some negative value of the output voltage, but now we are going to remove that with the help of freewheeling diode. So therefore we are going to increase the output average value also. We are trying to make the continuous conduction mode also. All these things are possible if you are trying to keep a freewheeling diode across the RL load. So from 0 to pi, diode D1 was conducting, and from pi to 2 pi, diode D2 is conducting. So now we are going to analyze this circuit. So from 0 to pi, I already told you from 0 to pi, diode D1 is conducting and diode D2 is off. Means diode D1 is forward bias and diode D2 is reverse bias, because Vs of t is greater than 0. So because of that, diode D1 is forward bias and diode D2 is reverse bias. So therefore, whatever the load voltage is equal to source voltage. So V naught of t is equal to Vs of t, and also the load current is equal to source current also in this case. Whereas from pi to 2 pi, diode D1 is reverse bias because Vs is less than 0. So because of that, diode D1 is reverse bias, whereas diode D2 is forward bias. So because of that, we can say that the load voltage is equal to 0. So the load voltage is equal to 0. So therefore now here source current is equal to 0 again, because the current is only flowing through freewheeling diode. So now the source current is equal to 0 in this case, whereas in the previous case the source current is equal to load current, but here now the source current is going to become 0. Now we will discuss the advantages of the freewheeling diode. See, continuous conduction mode is possible. With the help of freewheeling diode, we are trying to make the load current non-zero for all the time. So therefore, continuous conduction mode is possible if you are trying to keep the freewheeling diode across the RL load. And V0 is always positive, so V0 always increases, because we are trying to, means as there is no negative value of the output voltage, means we are increasing the average value of the output voltage. So because of that, V0 average is going to get increased. So V0 is always positive, so because of that, V0 average is also goes on increases. And output average power is equal to V0 average into I0 average. So if V0 average increases, then definitely their product is also goes on improves or increases. So we can say that as V0 average value increases, their product is also increases, means the average power, output power is also goes on increases. And now here, as already I told you, we are assuming that there are no losses in the diodes. So whatever the input power is equal to output power. So Vs RMS into Is RMS into cos phi is equal to V0 average into I0 average. So we can say that the power factor cos phi is called as the input power factor. It is directly proportional to the output average power. So the power factor is always directly proportional to the output average power. So therefore we can say that as the output average value increases, as the output voltage average value increases, then the input power factor is also increases. So as output average value increases, then the power factor is also increases. So because of keeping the freewheeling diode across the RL load, we are going to make the continuous conduction mode, and the average value of the output voltage increases. So because of that, the input power factor is also improves. So these are the three advantages we are going to get if you keep a freewheeling diode across the RL load. So now the circuit turn-off time. The circuit turn-off time is, here we are trying to find during what time, up to what time period we are going to keep a reverse voltage across the main diode. for main diode, we are going to keep a reverse voltage from pi to 2 pi. So the angle difference is 2 pi minus pi is equal to pi. But we want only time, so divide by omega. So pi by omega is the circuit tone name of the main diode D1. And if you want to know what is the average value of the output voltage, which is equal to, because there is only one pulse from 0 to pi, its value is equal to Vm by pi. So Vm by pi is the output average value. So output average value is equal to Vm by pi, whereas output RMS value is equal to Vm by 2. And here source current is not at all equal to load current in this case, because here source current is equal to load current only from 0 to pi, but after pi both are different. So we can say that now here the source current is not at all equal to load current in this case. And the peak inverse voltage of the diode main diode D1 is equal to Vm. So Vm is the peak inverse voltage across the diode D1, as I have already told you. So this is the analysis of this circuit. So now we are going to analyze this RE load. So we are going to keep an RE load now here across this one. Remaining everything is same, which is the source voltage, source current, diode, so plus or minus Vd of t, and here output current I naught of t, and this is the load of RE load, and which is plus or minus V naught of t. So now we are going to analyze this circuit. You can see clearly the diode is on only. The diode is on only when Vs is greater than E, then only the current is going to get passed. So then only we can say that the current is a positive only when Vs is greater than E. Then when the current is positive means the diode is on. So therefore when Vs is greater than E, the diode is on. Otherwise the diode is off. So now we are going to analyze the graphs of each and every thing. So now I am going to assume that the value of the E, the value of the voltage in the load is less than Vm. Then only the diode is going to get conduct. Otherwise the diode is not going to get conduct. So E is always less than Vm. So I am going to draw the first the source voltage. The source voltage waveform I am going to draw, which is Vs is equal to Vm into sine omega t. So this is the graph we are going to get. And now I am going to assume the E is less than Vm. So as I have already told you, from whenever the Vs is less than E, then the diode is off. Whenever the diode is off, then what is going to happen? Then we can say that the current, the output current is equal to 0, and also the output voltage is equal to E value. So therefore for this region its value, the output voltage is equal to E and the output current is equal to 0. Whereas from theta to pi minus theta, let me assume at an angle of theta we are going to get a value of E. From theta to pi minus theta, because the symmetry, if this is theta, this is also theta, so overall angle is equal to pi minus theta. So from theta to pi minus theta, here the source voltage is greater than E, it indicates that the diode is on. As the diode is on, we can say that the load voltage is equal to source voltage, so it is going to follow the source voltage in this region. And then as the diode is on, current is going to get increased, so current is going to get increased in this format from theta to pi minus theta. Again from pi minus theta, after that again Vs is less than E. If Vs is less than E means diode is off. As the diode is off, then we can say the output voltage is equal to E and the output current is equal to 0. So therefore here output voltage is equal to E and the output current is equal to 0. So these are the graphs we are going to get. Again same repetition is going to get happen after the 2 pi also. So now I will draw the voltage across the diode. As I already told you, from 0 to theta, Vs is less than E. As the Vs is less than E means the diode is off. As the diode is off means the output voltage is equal to 0. It indicates that whatever the diode voltage is equal to source voltage, or we can say if you take plus Vs of d and minus Vd of t minus V naught of t is equal to 0. So therefore now here what is going to happen? See here, whenever the diode is off, then V naught is equal to E. So therefore what you are going to get finally, Vd of t is equal to Vs minus E. So Vs minus E we are going to get in this region. So if you draw that graph, we are going to get in this format. So in this format we are going to get a negative voltage, which is Vs of t minus E is equal to Vd of t. So if you draw this, we are going to get in this format, because when Vs is equal to 0 we are going to get minus E, and when Vs is equal to E we are going to get E minus E is equal to 0. So we are going to get in this format. Whereas from theta to pi minus theta, the diode is on. So therefore, we are going to get here the diode voltage is equal to 0. Again from pi minus theta, the diode is off. So therefore, again we are going to get in this format. So which is again same Vs of t minus E. So Vs of t minus E means here simply we can say that at this peak value, we are going to get Vs is equal to minus Vm and minus E. So minus of Vm minus E is equal to minus of Vm plus E. So this is the peak inverse voltage of the diode. So peak inverse voltage of the diode we are going to get in this format, which is Vm plus E is called as the peak inverse voltage of the diode. So you can see clearly from circuit turn of time means from pi minus theta to 2 pi the voltage is negative, and from this 0 to theta also we are going to get a reverse voltage across the diode. So for this much amount of angle, which is 2 pi minus of pi minus theta plus for this region also theta. So this is called as a pi. From pi to pi is pi and this is theta. So pi plus theta plus theta. So overall pi plus 2 theta. So this is the amount of angle for which the voltage is reverse bias. So therefore pi plus 2 theta by overall angle is omega. So you are going to get the circuit turn of time. So for this much amount of time, the reverse voltage across the diode is going to get occur, which is DC is equal to pi plus theta by omega. So this is a circuit turn of time of the diode. So now we are going to analyze this circuit from 0 to pi. From 0 to pi, here what you are going to get is we are going to split into three parts. From 0 to theta and theta to pi minus theta and pi minus theta to pi. So here 0 to theta, as Vs is less than E, so diode is off or reverse bias. So whatever the output voltage is equal to voltage across that one means E, induced value means the source means the load voltage is equal to E. So V0 is equal to E. Whereas from theta to pi minus theta, the source voltage is greater than E. So therefore diode is forward bias. So current is equal to means you can say that the load voltage is equal to source voltage. V0 of t is equal to Vs of t, and load current is equal to output voltage minus E by R. Output voltage minus E by R. But the output voltage is equal to source voltage, which is Vs of t minus E by R. Whereas from pi minus theta to pi, from pi minus to theta to pi, what you are going to get basically, again the source voltage is less than E means the diode is reverse bias. As the diode is reverse bias, then definitely the load voltage is equal to E and the load current is equal to 0. And similarly from pi to 2 pi, again Vs is less than E. As Vs is less than E means simply we can say diode is reverse bias. As the diode is reverse bias means output current is equal to 0 and the output voltage is equal to E. So peak inverse voltage of the diode is equal to Vm plus C. Just now I have already told you. And the conduction angle of the diode. Conduction angle of the diode is for what angle the diode is conducting, which is pi minus theta. It is conducting from theta to pi minus theta. So the angle difference of angle is pi minus theta, which is pi minus 2 theta. Only for this much amount of angle the diode is conducting. And we are going to get a maximum value of the current at theta is equal to pi by 2. At pi by 2 we are going to get the maximum value of the current. So now I want to find what is the average value of the current. So average value of the current is equal to, which is 1 by 2 pi integration, because from theta to pi minus theta only the current is going to present, and the current expression which is here V0 is Vs of t minus E by R. So which is Vm into sin omega t minus E by R into d theta is equal to, so if we solve this one, finally we are going to get 1 by 2 pi R into 2 Vm cos theta minus E of pi minus 2 theta. So this is called as the average value of the output current we are going to get, which is 1 by 2 pi R into 2 Vm cos theta minus E of pi minus 2 theta. So this is the expression of the average value of the output current, which is 1 by 2 pi R into 2 Vm cos theta minus E of pi minus 2 theta. So you can easily do the simplification. Whereas output average value is equal to I0 average value into R plus E. So V0 average value is equal to I0 average into R plus E. And here always there are no extra branches, so therefore always the load current is equal to source current. So its average values are equal and also RMS values are equal. So I0 RMS is equal to IS RMS and I0 average value is equal to IS average value. And here, as I have already told you, the losses in the ideal diode are 0. So therefore whatever the input power is equal to output power. So input power is equal to Vs RMS into Is RMS into cos phi is equal to, here output power is equal to, simply we can say that I naught RMS square into R plus VE into I naught average. So VS RMS into IS RMS into cos phi is equal to I naught RMS square into R plus E into I naught average. So VS RMS into IS RMS cos phi is equal to I naught RMS square into R plus E into I naught average. So cos phi is equal to, finally we are going to get I naught RMS square into R plus E into I naught average by VS RMS into IS RMS. So this is called as the input power factor. So this is called as the input power factor. So input power factor is equal to I naught RMS square into R plus E into I naught average by VS RMS into IS RMS. So this is called as the input power factor. So now I want to find what is the RMS value of the output voltage. So RMS value of the output voltage is equal to under root over 1 by 2 pi. 1 by 2 pi integration of 0 to theta. Its value is equal to E. So E square into d theta plus from theta to pi minus theta. Theta to pi minus theta, which is Vm sin theta whole square into d theta plus again from pi minus theta to 2 pi, again its value is equal to E. So E square into d theta. So if you solve this one, we are going to get this complex expression, which is 1 by 2 pi of E square into pi plus 2 theta plus Vm square by 2 into pi minus 2 theta plus Vm square by 2 into sin theta over the power of 1 by 2. So this is the RMS value we are going to get. So whereas if you want to know what is the RMS value of the output current, which is here V dot RMS minus E by R, because V dot RMS is equal to I dot RMS into R plus E. So therefore I dot RMS is equal to V dot RMS minus E by R. So simply if you know I dot average, then we can figure out the V dot average. If you know V dot RMS or V dot RMS, we can get the another one from this expression. So whereas here sin, so I have already told you Vs of t is equal to Vm sin omega t. So at angle of theta, we are going to get Vs of t is equal to E. So therefore E is equal to Vm sin theta. So theta is equal to sin inverse of E by Vm. So theta is equal to sin inverse of E by Vm. So at this angle, we are going to get source voltage is equal to E value. So therefore theta is equal to sin inverse of E by Vm. So these are the some of the important analysis of this RE load. So now we are going to analyze this circuit. So this here, now we are going to keep RLE load. The previous case we have studied only RE load, but now we are going to keep an extra inductor here. So RLE load. So this is the same source voltage Vs of t, source current Is of t, and this is the diode. Here we are going to keep a I naught of t, and this is the load voltage, which is plus or minus V naught of t. So this is the output voltage, which is plus or minus V naught of t. So now we are going to draw the waveforms of this circuit. So this is the source voltage, which is Vs of t, which is equal to Vm sin omega t. So we are going to get in this fashion. And here I have already told you the E is less than always Vm. So therefore E is always less than Vm. And let me assume the angle is theta here. So I have already told you from 0 to theta, means from 0 to theta the source voltage is less than E. As the source voltage is less than E, it indicates that the diode is off. As the diode is off, then what is going to happen? The load voltage is equal to 0. The load voltage is equal to E value. The load voltage is equal to E, and the load current is equal to 0. So the load current is equal to 0. Whereas the voltage across the diode, D is equal to, which is here Vs of t minus V naught of t. So Vs of t minus V naught of t is equal to voltage across the diode. Therefore now Vs of t minus E. So therefore my Vs of t minus E, if you draw this one, we are going to get, this is the voltage across the diode. So you are going to get in this format, you are going to get. Then from 0 to now here it will be from up to angle beta. So because of inductor, from theta to beta, the means the diode is going to get conduct. But previously only from theta to pi minus theta the diode was conducting. But now from theta to beta the current is going to get conduct, or we can say the diode is going to get conduct because of the inductor. So because of that the current is going to increase, and finally it is going to decrease and becomes 0 at the angle of beta. So from theta to beta the diode is going to get conduct. So therefore when the diode is conducting, whatever the source voltage is equal to load voltage. So it is going to blindly follow the source voltage up to angle beta. So in this period, as the diode is conducting, means the voltage across the diode is equal to 0. So now here up to beta the diode is conducting, so its value is equal to 0. Again from beta the current is equal to 0. As the current is equal to 0 means here the diode is off, means the current wants to become negative. So because of that here, because of negative voltage, the diode is going to become negative, or you can say that the diode is reverse bias. So as the diode is reverse bias, then what is going to happen? Simply you can say that it is open circuit. If it is open circuit means simply the output voltage is equal to E value, the output voltage is equal to E, whereas the output current is equal to now 0. So then you always equal to 0 from beta to 2 pi. As here now the diode voltage is equal to source voltage minus output voltage. Again Vs of t minus E in this region we are going to get, if you draw this one we are going to get in this format, and this value which is minus Vm minus E is nothing but minus of Vm plus E. So peak inverse voltage of the diode is equal to Vm plus E. So this is the graph we are going to get. Everything is same, the only difference is here now the diode is going to connect from theta to beta, only because of inductor that the diode is going to conduct from theta to beta, and remaining everything is same as the previous one. So therefore, so this is the analysis of this circuit. So this is the diagrams of the circuit. So you can see clearly from here, you can find anything. So only from this theta to beta only the diode is going to get conduct, and remaining everywhere it is reverse bias, and the current is going to only flow from theta to beta. And so this is the analysis of this circuit. So with the help of this one we are going to move forward for the which is single phase half wave control rectifier. Up to now we have studied the single phase half wave uncontrolled rectifier with the R load, with the L load, with the RL load, and also we studied the RL load with the freewheeling diode, and also we studied the RE load and also RLE load. So basically we have studied the 6 types of loads. So now we have completed the single phase half wave uncontrolled rectifier, means we have kept the diode, but now we are going to study the single phase half wave controlled rectifier. Now we are going to study. So up to now we have discussed about the single phase half wave uncontrolled rectifier, different types of loads we have studied. So now we are going to study the single phase half wave control rectifier. Means the same loads we are going to study, but the only thing is we are going to we are going to interchange the diode by the we can say thyristor. So we have replaced the diode by thyristor, and the remaining loads are same. So now we are going to analyze this one in a very detailed manner. So half wave, single phase half wave control rectifier means we are going to keep the thyristor here. So you can say this is the source voltage plus or minus Vs of t, the source current is Is of t. So now we are going to analyze for the R load. So we are going to analyze for the resistive load. So this is a thyristor. So here this is I naught of t load current, and then let me assume this is plus or minus. So this is thyristor voltage which is plus or minus Vt of t, and this is the output voltage plus or minus V naught of t. So now we are going to find the different types of voltages, currents and expressions, everything we are going to study. See, these things I have already told you. Form factor is equal to, the easy way to remember is FRA, which is ratio of RMS value by the average value, which is output RMS value by the output average value. Means we are going to find what is the form factor of the output voltage. If you want ripple factor, which is under root over form factor whole square minus 1. So these are the formulas which I have already told you. So now here there is the input voltage is Vs of t, which is Vm sin omega t. So this is the curve we are going to get. So for up to pi it is a positive, from pi to 2 pi it is negative. So now as it is a thyristor, means here the firing angle alpha is going to lie between 0 to 180 degree, means the on we are going to on the thyristor based on our control. See, we can on it in the region of 0 to pi only. Only in the positive cycle only we can on the thyristor, but not in the negative cycle. In the negative cycle it is going to become reverse bias, so we cannot turn on it. So we can only on when the VAK is positive and the IG is positive, then only we are going to on that thyristor, otherwise we are not going to on it. Means only in the positive cycle, when VAK is positive and the IG is positive, then only the thyristor we can on it. So now the operation is from 0 to pi only, we can on it in this region up at any angle from alpha range from 0 to 180 degree. Let me assume at some alpha I am going to give the triggering gate pulse to the thyristor. So at this instant only it is going to become on. So we can say that from 0 to alpha, you can say that the thyristor in the forward blocking mode. In the forward blocking mode, what is going to happen? It acts like open circuit. So therefore, if it is open circuit, then we can say the output voltage is equal to 0. If the output voltage is equal to 0, then definitely output current is also 0 because it is acting like open circuit. Whereas from alpha to pi, what is going to happen? We have given the triggering at alpha, so it is going to become on. So when the thyristor is on, we can say that whatever the output voltage is equal to the input voltage, so it is going to follow the input voltage from alpha to phi. Then the output current is equal to output voltage by R. So we are going to get the peak value of Vm by R. Like this we are going to get the waveform of V of t and I of t are same for a resistive load. So from pi to 2 pi, we can say that the thyristor is in the reverse bias, so therefore it is going to act like a open circuit. So in that region, then definitely the output voltage is equal to 0 and output current is also equal to 0 because it is going to act like a open circuit. So it is going to become 0. Output voltage is 0 and the output current is also 0. So if you want to draw the thyristor voltage in all this region, from 0 to alpha it is in the forward blocking mode, means it is acting like open circuit. Then as output voltage is equal to 0, then whatever source voltage is equal to the thyristor voltage as per the KVL. So we are going to get the same voltage. Whatever the source voltage in this 0 to alpha, same will be across the thyristor also. Whereas from alpha to pi, the thyristor is in the on condition, so its voltage is equal to 0. Whereas in pi to 2 pi, it is going to act like open circuit. Then output voltage is equal to 0 in this region. So whatever the input voltage is equal to voltage across the thyristor as per the KVL, again it is going to follow the source voltage. Again minus Vm. So you can see that here it is going to have peak inverse voltage of Vm. See, from pi to 2 pi, it is going to face a reverse voltage or reverse breakdown voltage it is going to face. So only from pi to 2 pi, it is going to face the negative voltage. So you can see clearly here in the output there is only one pulse. So it is called as a one pulse converter. So only there is output. In the output there is only one pulse. So it is called as a one pulse converter. So now we are going to do the analysis of this circuit. So from 0 to alpha, I have already told you the thyristor is in the forward blocking mode. It means it is going to face the positive voltage. So it is in the forward blocking mode. So output voltage is equal to 0, means it is going to act like open circuit. So our output voltage is equal to 0 and the output current is 0. And here, based on the KVL, we are going to get whatever the thyristor voltage is equal to voltage across the voltage of the supply. So now here in this 0 to alpha, so output current and the input current are same because there are no extra branches. So source current is equal to load current always. From alpha to pi, as we are going to give the triggering for the SCR, so it is going to become on. So it is going to be in the conduction mode. So therefore it is going to act like an on switch. So whatever the output voltage is equal to input voltage and the output current is equal to output voltage by R or simply source voltage by R. And here, as it is in the on condition, the voltage across the thyristor is equal to 0 ideally. Whereas from pi to 2 pi, the thyristor is going to face a negative voltage. So it is in the reverse blocking mode. So it is going to act like an open switch. So therefore, the current output current is equal to 0 and the output voltage is equal to 0 and whatever the thyristor voltage is equal to the supply voltage because by the help of KVL. So now circuit turn off time. I have already told you circuit turn off time means the time for which the thyristor is going to face the reverse voltage or negative voltage. Only from pi to 2 pi it is going to face the negative voltage. So 2 pi minus pi is pi. So pi by omega, only for this much amount of time it is going to face the negative voltage. Whereas I have already told you there is no extra branch. So therefore whatever the source current is equal to load current. So RMS value of the source current is equal to RMS value of the load current and the average value of the source current is equal to average value of the load current. And if you want to know what is the output average value expression, so output voltage average value is equal to 1 by 2 pi integration of alpha to pi Vm sin theta into d theta. So if you do the simplification of this, we are going to get Vm by 2 pi into 1 plus cos alpha. So Vm by 2 pi into 1 plus cos alpha we are going to get. So Vm by 2 pi into 1 plus cos alpha is the average value of the output voltage we are going to get. And I have already told you the output average value is equal to V naught average is equal to I naught average into R. So therefore I naught average is equal to V naught average by R. So therefore if we substitute here, we are going to get Vm by 2 pi R into 1 plus cos alpha. So if you want to find what is the RMS value of the output voltage, RMS value of the output voltage is equal to under root over 1 by 2 pi integration of alpha to pi Vm sin theta whole square into d theta. So if we solve this one, we are going to get Vm by 2 into under root over 1 by pi into pi minus alpha plus sin 2 alpha by 2. So Vm by 2 into under root over 1 by pi into pi minus alpha plus sin 2 alpha by 2. So this is the expression of the RMS value of the output voltage, which is Vm by 2 into 1 by pi into pi minus alpha plus sin 2 alpha by 2 we are going to get. Whereas the output average value is equal to Vm by 2 into 1 plus cos alpha. Whereas output voltage RMS value is equal to Vm by 2 into 1 by pi into pi minus alpha plus sin 2 alpha by 2 we are going to get. So now we are going to find what is the average power absorbed by the load, which is the average active power absorbed by the load is equal to V naught RMS square by R is equal to I naught RMS square into R. So therefore I naught RMS is equal to V naught RMS by R. So the amount of average power absorbed by the load is equal to I naught RMS square into R or V naught RMS square by R, whereas V naught RMS is equal to I naught RMS into R. So I already told you here simply that there are no losses by the in the thyristor. So therefore whatever the input power is equal to output power. So Vs RMS into Is RMS into cos phi is equal to I naught RMS square into R, because this is the average, we can say average input power in the source denoted by the source, whereas this is the average power absorbed by the load. So they both have to be equal. So Vs RMS into Is RMS into cos phi is equal to I naught RMS square into R. I already told you the supply, so Is RMS is equal to I naught RMS. So they are going to get cancelled one term. Finally we are going to get cos phi is equal to I naught RMS into R by Vs RMS. So I naught RMS into R is nothing but V naught RMS. So V naught RMS by Vs RMS. So cos phi is called as the input power factor, which is V naught RMS by Vs RMS. Already we know the value of V naught RMS, and Vs RMS is Vm by root 2. So this by this we are going to get the input power factor. And the conduction angle of the thyristor means for what angle the thyristor was conducting. So thyristor is conducting only from alpha to pi. So the range is pi minus alpha. Only for this pi minus alpha the thyristor is conducting. And here if you want to know what is the extinction angle, means the angle at which the load current is going to become 0. The load current is going to become 0 at omega t is equal to pi. So at pi angle the I naught of t is going to become 0. So this is called as the pi. So whereas peak inverse voltage is equal to Vm for the thyristor, and Fr is called as the number of pulses into Fs. So Fr is called as the ripple frequency or the output frequency. So ripple frequency or output frequency is equal to number of pulses into Fs, or simply we can say output frequency in the voltage or output frequency of the output current. So ripple frequency or the frequency in the output voltage or the output current is equal to number of pulses into supply frequency. So as there are only one number of pulses, so only one pulse are going to present in the output voltage or current. So it is 1. So 1 into Fs. So we can say this is, so Fr is equal to Fs in this case. So simply we can say that Fr is called as the ripple frequency or the output frequency, whereas Fs is called as the supply frequency. Also ripple frequency is equal to number of pulses into supply frequency. As there are only one pulses in this case, so 1 into Fs is Fs. So if you want to know what is the normalized output voltage, normalized output voltage is Vm. So Vm is equal to average value of the output voltage at any firing angle by average value of the output voltage at alpha is equal to 0. So normalized output voltage means it is the ratio of the average value of the output voltage at any firing angle by average value of the output voltage at alpha is equal to 0. So if we do simplification of this, we are going to get 1 plus cos alpha by 2. So this is called as the normalized output voltage, means it is the ratio of the output average voltage at any firing angle by output average value at alpha is equal to 0. So we are going to get normalized output voltage is equal to 1 plus cos alpha by 2, and the peak inverse voltage is equal to Vm, and the peak inverse voltage is equal to the maximum amount of voltage, that means the maximum reverse voltage experienced by the thyristor is Vm. So Vm is the correct solution of this question. So this is the Vm. So I've already told you form factor is equal to, it is the ratio of RMS value by the average value. So basically we are going to find what is the form factor in the output voltage, which is B naught RMS by B naught average, whereas ripple factor is equal to under root over form factor whole square minus 1. So now we are going to learn for the another case of L load. So now we are going to apply the L load. So then what is going to happen, we are going to see. So this is the source voltage Vs of t and the source current is Is of t, and the thyristor voltage which is plus minus Vt of t, and this is output current I naught of t, and this is the output voltage V naught of t, and this is the inductor L. So this is plus minus Vt of t. So plus minus Vt of t is the voltage across this thyristor. So now we are going to analyze the diagrams of this circuit. So here we are going to apply source voltage of Vm sin omega t. So this is the waveform we are going to get, Vm sin omega t with a peak value of plus Vm and minus Vm. As I have already told you, we can on the thyristor only in the region of 0 to pi, because in this region only the voltage, the source voltage is positive. So only in this region we are going to on the thyristor. So this is the triggering angle or the gate current we are going to give at a certain angle of alpha. So alpha ranging from 0 to 180 degree only. So here from 0 to pi, we can say that we are not given the triggering angle, so the thyristor will be in the forward blocking mode. Then why it is going to act like open circuit, so therefore output voltage is equal to 0. So output voltage is equal to 0. It means that output current is also 0 in that case. Whereas from alpha we are going to give the triggering, so it is going to act like a on. So it is going to act like a on means whatever the output voltage is equal to source voltage. So therefore it is going to become whatever the output voltage is going to same become the source voltage. So output voltage is equal to source voltage. Region we can say that from alpha to pi the inductor is going to become charged, because Bs is positive, so the current is going to become positive. It is going to in charging mode. So therefore now from pi to 2 pi minus alpha. So from pi to 2 pi minus alpha, if this is alpha, this is also alpha, so this angle will be, overall angle will be 2 pi minus alpha, means here this will be from pi to 2 pi minus alpha. So for this region also it is going to become, it is going to act like a, the thyristor is going to act like a on position. So because of that here now the current is going to become decay, because negative voltage is going to apply, so current is going to become slightly decreasing from pi to 2 pi minus alpha. So therefore in that region as the thyristor is on, so output voltage is equal to source voltage also. So it is also become same thing. So you can see clearly now average, I have already told you the average output voltage of the inductor will be always equal to 0, whereas the average of current in a capacitor is always equal to 0. So here average voltage across the inductor should be always equal to 0. So because of that, if this is positive area, here it should be negative area. Both should be symmetrical, then only overall area is equal to 0. So because of that, if this is pi to alpha, this is pi minus alpha, here also same angle of pi minus alpha you are going to get, then only symmetry we are going to get. So therefore the current is going to charging from alpha to pi, and from pi to 2 pi minus alpha it is going to get decay. So from 2 pi minus alpha to 2 pi it is going to act like an open circuit, means it is going to become like a, because negative voltage applied to the thyristor, it is going to act like an open circuit. So therefore again the output current is 0 and the output voltage is equal to 0. So now you will analyze the voltage across the thyristor in this case. I have already told you from 0 to alpha. From 0 to alpha the thyristor is in forward blocking mode. So therefore what means it is going to act like an open circuit. So output voltage is equal to 0. So whatever the source voltage should be equal to thyristor voltage. So it is going to follow the source voltage. From alpha to 2 pi minus alpha the thyristor is on. So therefore it is going to become like a short circuit, means like voltage across it is 0. Whereas from 2 pi minus alpha to 2 pi we have said that it is going to act like an open circuit. So whatever the voltage across the thyristor is equal to source voltage, again it is going to follow the source voltage. So this is the diagram we are going to get for each and every output voltage, output current and the voltage across the thyristor. So now we are going to do some analysis for this circuit. See, when the thyristor is on, we can say that the output voltage is equal to source voltage. So therefore Vm sin omega t is equal to L into di by dt. So if I do the rearrangement, I am going to get di is equal to Vm by L into sin theta dt. So therefore Vm by L into sin theta into dt, where current is going from 0 to I from time. The time is now alpha by omega to t. So very important point. See, for alpha by omega, then only current is 0 at that position. So from time alpha by omega, at the time the current is 0, again it is going to become current I at the time of t. So therefore here we have to go from integral alpha by omega to t, means integration 0 to I, because from alpha by omega only we are going to get a current of 0 value. Again up to t the current expression is I of t. So if you do a simplification of this one, we are going to get I of t is equal to Vm by omega L into cos alpha minus cos omega t. Means at this value of time t, the current in the inductor is, this is the expression, and this expression is only for alpha less than or equal to omega t less than or equal to beta. Then beta is equal to 2 pi minus alpha. Only in this region only this expression is going to get hold, which is alpha less than or equal to omega t less than or equal to beta. Beta is equal to 2 pi minus alpha. So we can say that here integration for t is equal to alpha by omega to t, and here I is equal to 0 to I of t. So from this only we are going to get the value of the expression, which is Vm by omega L into cos alpha minus cos omega t, where alpha, where omega t is lying between alpha to beta, where beta is equal to 2 pi minus alpha. See, if you want to find what is the extinction angle beta, if you want to find what is the extinction angle beta, means at what angle the current is going to become 0. So let me assume at omega t is equal to beta, the current in the circuit is going to become 0. So therefore if you substitute 0 at an angle of beta, cos beta, then we are going to get 0 is equal to Vm by omega L into cos alpha minus cos beta. So we are going to get cos alpha is equal to cos beta. It indicates that beta is equal to 2 pi minus alpha. So at this angle we are going to get the current in the inductor is equal to 0. So therefore this is the value of the extinction angle in the output current is equal to 2 pi minus alpha. And I have already told you the output average value across the inductor will be always equal to 0, because positive area is equal to negative area. So therefore it will be always equal to 0. As there is no extra branch, the output current is equal to source current. So its average value of the output current is equal to average value of the source current, and the RMS value of the source current is equal to RMS value of the load current. And if you want to find what is the conduction angle of the thyristor, up to what angle the thyristor was conducting, which is from alpha to 2 pi minus alpha it is conducting. So therefore 2 pi minus alpha you are going to get 2 pi minus 2 alpha. So for this range the thyristor is going to get conduct. So if you want to find what is the circuit turn off time, circuit turn off time means for what range the thyristor is going to have a reverse voltage. Only from 2 pi minus alpha to 2 pi. So only from 2 pi minus alpha to 2 pi it is going to face a reverse voltage. So simply we can say 2 pi minus alpha by omega, which is alpha by omega, or simply we can say 2 pi minus beta by omega, where beta is equal to 2 pi minus alpha. So only for alpha by omega, only for this range it is going to face a reverse voltage or the negative voltage. So the circuit turn off time, which is alpha by omega. And if you want to know what is the maximum, if you want to know what is the maximum value, if you want to know what is the maximum value of the current, then here we have to substitute omega t is equal to pi. The general expression is Vm by omega into cos alpha minus cos omega t. In omega t we have to substitute the pi. At that time only we are going to get the maximum value, which is Vm by omega L into cos alpha minus cos pi. So we can say this is the maximum value in the inductor, or we can say this is the maximum value of the current in the circuit. So cos phi is nothing but minus 1. So minus into minus is plus. So you are going to get Vm by omega L into 1 plus cos alpha. This is the maximum value of the current in this circuit. So now we are going to replace the L load by the R load. So previously we have studied for the R load, then L load, then we are going to study the RL load. See, this is called as a single phase off wave controlled rectifier. So single phase off wave controlled rectifier. So this is the source voltage plus or minus Vs of t, source current Is of t, and this is the thyristor voltage which is plus or minus Vt of t, and the load current is I naught of t, and the load is RL load, and the output voltage is plus or minus V naught of t. So based on this we have to find what is the output voltage, output current, everything we are going to find. The source voltage is Vm sin omega t. So we are going to get in this way, which is Vm sin omega t. For 0 to pi it is positive and pi to 2 pi it is negative. So here, as I have already told you, the alpha range means we are going to trigger, we are going to trigger the thyristor only in the range of positive cycle of the input voltage, which is 0 to pi. So alpha can drive between 0 to pi. For alpha is called as that we are going to use the triggering gate current pulse in the range of only 0 to pi, because only in this region the source voltage is positive. So now from 0 to pi, you can see clearly that in 0 to pi, as the source voltage, we can say that here, as we are not going to give any triggering, so it is going to act like open circuit. So whatever the source voltage is equal to thyristor voltage in that region, and we can say simply the load voltage is equal to 0 and the load current is also 0 in that case. So only from alpha we are going to use the triggering. So therefore now it is going to become the on. As it is going to become the on, then definitely the source voltage is equal to load voltage. So it is going to follow the load voltage is equal to source voltage. So therefore now it is going to become charging. If it's a pure R load, it has become maximum of pi by 2. If it is a pure L load, the current has become maximum at pi. But for RL load, it is going to become the maximum in the range of pi by 2 to pi. So from pi by 2 to pi, somewhere in between them, it is going to become maximum value. So in this, it is going to charging and then it is going to become discharged. So up to this region, from alpha to beta, the thyristor is going to get conduct. So because of that, what is going to happen? So from alpha to beta, it is going to conduct. The thyristor is going to get conduct region. So therefore, the load voltage is equal to source voltage in that range. So from alpha to beta, then the source voltage is equal to load voltage. It is going to get follow. So you can see clearly here from alpha to beta. Then after that beta, the current is 0. As the current was to become negative, but a current cannot be negative in the thyristor. So therefore current will be 0, means open circuit. And the thyristor is going to face the negative voltage. So because of that, we can say simply here it is going to act like open circuit. So therefore current will be always 0. So therefore as the switch is open, so the load voltage is also equal to 0 in that case. So from here to 2 pi, the load voltage and the load current are both are 0. So you can see clearly in the 0 to 2 pi, only one pulse is present. So it is called as a one pulse converter. So for now we are going to analyze the thyristor voltage in different ranges. So 0 to alpha, as I already told you, the thyristor in the forward blocking mode. So therefore the source voltage is equal to thyristor voltage. So therefore it is going to follow this one. Whereas from alpha to beta, we can say that here simply from alpha to beta, it is going to behave like a short circuit because it is in conduction. So its voltage is equal to 0. Whereas from beta to 2 pi, it is going to become like a open circuit. Again, the thyristor voltage is equal to source voltage. So whatever the source voltage, it is going to get blindly following. So peak inverse voltage is equal to Vm. And from beta to 2 pi only, this thyristor is going to face a negative voltage or the reverse voltage. So we can say the circuit turn of time is equal to 2 pi minus beta by omega. See, in this region from alpha to, in this region, the current is going to get increase or charging mode and then it is going to discharge. So because of this extra region only, it is going to become conduct. So it is going to have even a negative pulse. So now we are going to analyze this circuit. As I already told you, there is no extra branch between the circuit. So therefore, the source current is always equal to load current, means the average value of the source current is equal to the average value of the load current, and the RMS value of the source current is equal to RMS value of the load current. And if you want to know what is the circuit turn off time, I already told you only from the angle beta to 2 pi, the thyristor voltage is negative. So therefore, 2 pi minus beta by omega is the circuit turn off time. And the peak inverse voltage of the thyristor is equal to Vm. Just now I have told you. So from alpha to pi, I have already told you here from alpha to pi that V0 is greater than 0 and also I0 is greater than 0. So therefore period is greater than 0. So from alpha to pi, the output voltage is greater than 0 and the output current is also greater than 0. So if we product of these two things, then the period is also greater than 0. It indicates that load is receiving power from the source, or we can say source is delivering the power to the load. Or from pi to beta, the output voltage is less than 0, whereas the output current is greater than 0. So if it is the product of these two things, the output power is less than 0, it indicates that load is delivering power to the source. So we can say simply the source is absorbing the power. So from alpha to pi, we can say that the load is absorbing the power from the source, whereas from pi to beta, the load is delivering power to the source. And here I naught maximum means the maximum value of the output current can occur in the range of pi by 2 to pi. Only in this range, somewhere in this range, it is going to become maximum, because at pi by 2, current was maximum for the R load, whereas at omega t is equal to pi, the current was maximum in the L load. So if you go for the combination of these two things, then it will be somewhere in between pi by 2 to pi, the current will be maximum. So if you want to know what is the average output voltage, so average output voltage is equal to 1 by 2 pi into integration of alpha to beta Vm sin theta d theta. So if you solve this one, we are going to get Vm by 2 pi into cos alpha minus cos beta. It is a very important expression. So if you remember this general expression, you can apply it for anyone. You are going to get the simple results. So this formula you should remember to go for any easy manner. So Vm by 2 pi into cos alpha minus cos beta. So where beta is called as the extinction angle and alpha is called as the firing angle. So Vm by 2 pi into cos alpha minus cos beta, where alpha is called as the firing angle and beta is called as the extinction angle. So Vm by 2 pi into cos alpha minus cos beta. So Vm by 2 pi into cos alpha minus cos beta. As I have already told you, this because here V naught average is equal to I naught average into R plus BL average, where BL average means the voltage across the inductor is average value is always equal to 0. So therefore V naught average is equal to I naught average into R. So therefore I naught average is equal to V naught average by R. So therefore, as I already know the value of the output voltage average, we can substitute here. We are going to get Vm by 2 pi R into cos alpha minus cos beta. So if you know what is the average value of the output voltage, then we can easily figure out the output current average value also. We can easily figure it out. So now I want to find what is the output RMS value. So output RMS value is equal to under root over 1 by 2 pi integration of alpha to beta Vm sin theta whole square into d theta. So if you solve this one, finally we are going to get Vm by 2 into 1 by pi into beta minus alpha plus half of sin 2 alpha minus sin 2 beta over the power of 1 by 2. It's a very important formula. So if you remember the V naught average value and V naught RMS value, then we can apply this formula for any general circuit. So therefore, V naught average is equal to Vm by 2 pi into cos alpha minus cos beta, whereas V naught RMS is equal to Vm by 2 into under root over 1 by pi into beta minus alpha plus 1 by 2 into sin 2 alpha minus sin 2 beta. We are going to get like this. So Vm by 2 into under root over 1 by pi into beta minus alpha plus half of sin 2 alpha minus sin 2 beta. So if you want to know what is the conduction angle of the thyristor, the conduction angle of the thyristor means at what range of thyristor or at what range the thyristor was conducting, at what range of angle the thyristor was conducting. The thyristor was conducting from alpha to beta, so its angle difference is beta minus alpha. So for this beta minus alpha range only, the thyristor was in conduction mode, where alpha is called as the firing angle of thyristor and whereas beta is called as the extinction angle of the thyristor, means at this value the current output current is going to become 0. Whereas gamma is called as the conduction angle of the thyristor, means for what angle of range the thyristor was conducting, which is alpha is equal to beta minus alpha. So therefore we can say that the conduction angle of the thyristor is equal to beta minus alpha, where gamma is called as the gamma t or gamma is called as the conduction angle of thyristor, whereas alpha is called as the firing angle of thyristor, whereas beta is called as the extinction angle of thyristor, means at what angle the thyristor was in this, or we can say it is going to become off, or simply the current at that point is going to become 0. And ripple frequency is equal to the number of pulses into supply frequency, as there are only one number of pulses in the output voltage, so 1 into Fs is Fs. So this is called as the output frequency also. So now we are going to keep a freewheeling diode, which is RL freewheeling diode. So just now we have studied the RL load, but now we are going to keep this extra freewheeling diode we are going to keep, and everything is same. So therefore source voltage plus or minus Vs of t, source current Is of t, thyristor voltage is plus or minus Vt of t, and this is the load voltage V naught of t, and the load current is I naught of t, and this is the freewheeling diode. So now we are going to analyze each and every aspect in this circuit. So now as the source voltage is equal to Vm side omega t, we are going to get in this graph. So from 0 to pi it is positive and pi to 2 pi it is negative, with a peak value of plus Vm and minus Vm. As I have already told you, the thyristor can only be triggered in the positive cycle of supply voltage only from 0 to pi. So alpha can range from 0 to pi. At this value of alpha, we are going to give a positive gate pulse to this thyristor, so it is going to become positive or it is going to become on. Only when VT is means we can say the voltage across the anode and cathode is positive, means VAK is equal to positive, and then only if you give a positive gate pulse, then only it is going to become trigger. So now, as I already told you, from 0 to alpha, we are not going to give any triggering, as we are not going to give any triggering to this thyristor, so therefore it is going to become like off position. So whenever it is in off position, it is open circuit. So therefore the load voltage is equal to 0 and the load current is also equal to 0. Whereas from alpha we are going to give the triggering, so it is going to become like a on. So therefore it is going to charge. It is going to charge. It is going to become charging condition. So after pi, what is going to happen is here it is going to discharge, because we are going to give a negative supply voltage after the pi. So because of that, the current is going to decay. The current is going to decay, and after this beta, at this beta, the current wants to become negative. But a thyristor, a current cannot be negative. So therefore, it will be open circuit. So therefore, it will be open circuit. So only the thyristor is going to conduct only from alpha to beta. So therefore, as the thyristor is conducting only from alpha to beta, so therefore simply we can say in this range the output voltage is equal to source voltage. So therefore it is going to become like this. So only from alpha to pi, we can say that it is going to see from alpha to pi, it is the current is going to become charging mode. The current is going to become in charging mode. So therefore here it will be the source voltage is equal to load voltage. So therefore from alpha to pi. But after pi, what is going to happen is, after pi, here we are going to give a negative voltage. So as we are going to give a negative voltage, the thyristor is off, and also there is a freewheeling diode. So because of this freewheeling diode, it is going to become on. As the freewheeling diode is going to become on, so therefore the output voltage will be equal to 0. So output voltage will be equal to 0, but the current is going to get decay in a slow manner. So therefore here the main thyristor is conducting only from alpha to pi, means from alpha to pi the main thyristor is conducting, whereas from pi to beta the freewheeling diode is going to get conduct. So we can say that same for both CCM and DCM is continuous conduction mode and the discontinuous conduction mode. Whether the current is continuous conduction mode or discontinuous conduction mode, this graph is always going to become same. See, continuous conduction mode means this value is not at all equal to 0, means it will be always non-zero value. Whether it is a discontinuous conduction mode means the current is going to become 0 after some angle of beta. See, whether it is a CCM or DCM, always that main thyristor is going to conduct only from alpha to pi. So therefore this voltage will be always equal to this value. But after this, no matter whatever the value, whatever that is CCM or DCM, definitely freewheeling diode is going to get conduct. So therefore we can say its voltage is equal to 0. But here in this called as a DCM, discontinuous conduction mode, from pi to beta the freewheeling diode is going to get conduct. So after that, what is going to happen is simply we can say that from beta to 2 pi, as the thyristor is going to experience the negative voltage, then we can say the load current is also become 0, and also here as from beta to 2 pi the thyristor is going to experience the negative voltage, so its voltage is equal to 0. So output voltage is 0, and also the output current is also equal to 0. So let me draw what is the voltage across the thyristor and the output current, say source current. So thyristor current I already told you from 0 to alpha, here we are going to means from 0 to alpha we are not given any triggering, so therefore it is a forward blocking mode. So whatever the source voltage is equal to voltage across the thyristor, so it is going to become like this. Whereas from alpha to pi, as the main thyristor is going to get conduct, so therefore its voltage is equal to 0. Voltage drop across it is equal to 0. From pi to 2 pi, means from pi to beta, we can say simply that main thyristor is going to get, means from pi to beta the freewheeling diode is going to get conduct. But here whether, because from pi to beta the thyristor is going to experience a negative voltage, so therefore we are going to get pi to 2 pi. From pi to 2 pi, whatever the source voltage is equal to voltage across the supply voltage, so therefore we are going to get like this. So in this region the thyristor is off but the freewheeling diode is on, so because of that only we are going to get what of the source voltage is equal to voltage across the thyristor. So we are going to get in this format. So you can see that the circuit turn of time is equal to, yes, we can say only from pi to 2 pi the thyristor is going to experience a negative voltage. So we can say 2 pi minus pi is pi by omega. Circuit turn of time is the time for which the main thyristor is going to experience a negative voltage, which is pi by omega, and the peak inverse voltage experienced by thyristor is Vm. And if you want to know what is the source current, see, source current I have already told you, as there is an extra branch, so source current will never be equal to output current for all the time. So here only when the main thyristor is conducting, only for the region of main thyristor is conducting, both are going to be same. Whereas when the freewheeling diode is going to get conduct, then the source current is not equal to load current. So from alpha to pi, we can say that from alpha to pi, only the main thyristor is going to conduct and the freewheeling diode is off. So therefore, source current is equal to load current up to here. Whereas from pi to the remaining range, the freewheeling diode is conducting but not the thyristor. So thyristor is open. So therefore, the source current will be equal to 0. So therefore, now you can see this, these two are different graphs. Only from alpha to pi both are same, but after that this is non-zero, but this is 0. So these two are different graphs because of extra branches present. So now we are going to do some analysis of this circuit. So as because of extra branches there, so we can say that the source current is never equal to load current. So therefore, the source current RMS value is never equal to load current RMS value, and the source current average value is never equal to load current average value. And here V0 average is always positive. See, because here if V0 wants to be negative, if V0 wants to be negative, then definitely the freewheeling diode is going to get conduct. So because of that, the output voltage will be 0 in the negative region. So output voltage cannot be negative, because if it wants to be negative, then the diode is going to get conduct. The freewheeling diode is going to get conduct. So because of that, the V0 will never be negative. So V0 average always positive. So therefore, as the V0 average means as the output voltage is always positive, so therefore the V0 average value goes on increases. So V0 average value always positive, or it is going to get increased. So therefore the output power is also increases and the input power factor also improves. I have already told you, because of freewheeling diode, three things are going to happen. The output voltage is always positive, so therefore output average value increases, and the power, output power is equal to V0 average into I0 average. As the V0 average increases, then the output power I2 power is also goes on increases, and input power factor also I have already told you, which is input power factor is always directly proportional to V0 average. So therefore, as the power factor, input power factor also goes on improves. So these three things are going to happen with the help of placing the freewheeling diode. And the thyristor is going to conduct only from alpha to pi, whereas the freewheeling diode is going to conduct from pi to beta. From beta to 2 pi, everything is off. The thyristor is off and the freewheeling diode is also off. So therefore, the conduction angle of the thyristor is pi minus alpha, whereas the conduction angle of the freewheeling diode is beta minus pi for discontinuous conduction mode, from beta minus pi. Whereas for continuous conduction mode, what is going to happen is, for continuous conduction mode, it is going to conduct up to, it is going to conduct means current will never be equal to 0. So therefore, it is going to become 2 pi plus alpha minus pi. See, for continuous conduction mode, what is going to happen is basically here, for continuous conduction mode, the current will never be equal to 0. So therefore, simply we can say that for 0 to alpha, the freewheeling diode is going to conduct. Again from pi to 2 pi also it is going to get conduct. So listen carefully. From 0 to alpha, the freewheeling diode is going to get conduct. Again from pi to 2 pi also, the freewheeling diode is going to get conduct. So the overall range is pi plus alpha. So for a period of pi plus alpha, the freewheeling diode is going to conduct, whereas from pi minus alpha, for this range, we are going to conduct the main thyristor. So listen carefully. So beta minus pi for discontinuous conduction mode, the conduction angle of the freewheeling diode. Whereas for continuous conduction mode, for 0 to alpha, the freewheeling diode is going to get conduct. Again from pi to 2 pi, the freewheeling diode is going to get conduct. So overall value, which is pi plus alpha. So for a pi plus alpha, the freewheeling diode is going to conduct for the continuous conduction mode. And for both these cases, this value is same, which is pi minus alpha. The conduction angle of thyristor, which is pi minus alpha. So if you want to find what is the average value of the output voltage, so average value of the output voltage is equal to 1 by 2 pi into integration of alpha to pi Vm sin theta into d theta. So if you solve this one, we are going to get Vm by 2 pi into 1 plus cos alpha. But if you know the general expression, which is Vm by 2 pi into cos alpha minus cos beta, but here beta is equal to 2 pi, means here beta is equal to pi, because here simply means in place of only V naught of t I am going to tell you, only in the case of V naught of t. So therefore beta is equal to pi if you substitute. So cos alpha minus cos alpha minus cos pi, which is cos pi is equal to minus 1. So minus into minus is plus. So we are going to get Vm by 2 pi into 1 plus cos alpha. So this is the expression we are going to get here. And I have already told you, if you want to know what is the I naught average. So V naught average is equal to I naught average into R plus VL average, but VL average is equal to 0. The average value of the electrovoltage is equal to 0. So therefore V naught average is equal to I naught average into R. So therefore I naught average is equal to V naught average by R. As you have already know the value of the V naught average, you can substitute here. So you can get the value of the I naught average. So therefore simply, if you know the output voltage average value, simply by this expression we can get even the output current average value. And the input power is always equal to output power, because we are going to assume the losses in the thyristor and the freewheel diode are 0. So therefore the input power is equal to output power. Input power is equal to Vs RMS into Is RMS into cos phi. As see here Vs of t, let me assume Vs of t is equal to Vm sin omega t. See, because the source current, see basically the source current is a periodic waveform, because here this is for a 2 pi, but as the time goes on it is basically periodic signal. So therefore we can say that if you write it in terms of sine and cosine, we are going to get, let me assume this is the expression we are going to get, which is I naught plus Im1 sin omega t plus Im2 sin 2 omega t, and goes on. So therefore P input power is equal to so here P input power is equal to, take only the fundamental values, which is Vs RMS into Is1 RMS into cos phi 1. So therefore this we are going to call it as this is the fundamental, or we can say input power due to fundamental component, which is Vs RMS into here Is1 RMS into cos phi 1, where phi 1 is the angle between the input voltage and the fundamental input current. So now we can equate both the things. So therefore Vs RMS into Is1 RMS into cos phi 1 is equal to Vs RMS into Is RMS into cos phi. As with both are same, so they are going to get cancelled. So therefore cos phi 1 is equal to Is RMS by Is1 RMS into cos phi. So here if you rearrange this one, we are going to get cos phi is equal to Is1 RMS by Is RMS into cos phi 1. So this is called as the RMS value of the fundamental component by the overall RMS value of the current. This is called as the distortion factor. So the RMS value of the fundamental component by the RMS value of the total current is called as the distortion factor G. The distortion factor is G, and this is called as the cos phi 1. This is the angle phi 1 is the angle between the current voltage and the fundamental component of the current. So therefore we can say this is a fundamental power factor. So therefore G into FDF. So input power factor is equal to distortion factor into fundamental power factor. It's a very important relation. So input power factor is equal to distortion factor into fundamental power factor. So here basically there will be a small amount of angle phi 1. So here this will be Im1 sin omega t minus phi 1 it will be actually, but I am not written here. It will be Im1 into sin omega t minus phi 1. So if you want to know what is the input power, so Vs RMS into Is1 RMS into here cos phi 1. So you are going to get here basically cos phi 1, where phi 1 is the angle between the, so this is Im1 sin omega t minus phi 1. So like this we are going to get. So Vs RMS into Is1 RMS into cos phi 1 is equal to Vs RMS into Is RMS into cos phi. So these both are same, they are going to get cancelled. So therefore if you rearrange this one, cos phi is equal to Is1 RMS by Is RMS into cos phi 1. This is called as the distortion factor into fundamental power factor. So therefore this is called as the distortion power factor into fundamental power factor, where phi 1 is the angle between the fundamental component of the supply voltage and the fundamental component of the source current. So where phi is the overall angle between the supply voltage and the supply current, whereas phi 1 is the angle between the supply voltage and the fundamental component of the source current. So Vs RMS is equal to Vm by root 2, whereas Is1 RMS is equal to Im1 by root 2. So always remember, input power factor is equal to distortion factor into fundamental displacement factor. So cos phi input power factor is equal to distortion factor into fundamental power factor. So G is called as the ratio of the fundamental RMS value of the current by the overall RMS value of the current into here cos phi1. Phi1 is the angle between the fundamental component of the source voltage and the fundamental component of the source current and the source voltage. So here Vs of d is equal to Vm sin omega t, and Is of t will be, have a small correction here, I0 plus Im1 sin omega t minus phi1 plus Im2 sin of 2 omega t minus phi2, and it goes on. So this is the periodic waveform, in the periodic waveform of writing this Is of t waveform. So now we can say that here phi1 is the angle between the power factor angle between the Vs of t and the Im1 of t. So therefore we can say that Vs RMS into Is1 RMS into cos of phi1 is equal to Vs RMS into Is RMS into cos phi. So these both are equal, so we are going to cancel. So cos phi is equal to Is1 RMS by Is RMS into cos phi1. So this is called as distortion factor, and this is the fundamental factor. So everything is same, just added the small correction, which is Is of t is equal to I0 plus Im1 sin omega t minus phi1 plus Im2 sin of 2 omega t minus phi2, and it goes on. So now we are going to study the RE load. Another of RE load. So this is the source voltage plus or minus Vs of t, and the source current is Is of t, and the load current is I0 of t, and this is the thyristor. Thyristor voltage is equal to plus or minus Vt of t, and the load is now RE load. So the output voltage across the load, which is plus or minus V0 of t. So now we are going to draw the graph of each and every parameter, and we are going to analyze this circuit. So as the source voltage is equal to Vm sin omega t, so this is the graph we are going to get. So now I am going to assume that E value is always lesser than the peak value of the source voltage, which is E is always less than Vm. So E is always less than Vm, so therefore E we are going to get, so draw a straight line here. So now here that angle theta, so this is the angle theta, theta is equal to sin inverse of E by Vm. Theta is equal to sin inverse of E by Vm. So now here only from theta to pi minus theta, we have the opportunity to trigger the thyristor only in this range. So therefore alpha is going to vary from theta to pi minus theta only because in this region only the source current can be positive only in this region only, but not the outside of this region. So therefore alpha can only vary from theta to pi minus theta. So therefore now let me assume at an angle of alpha in this range I am going to trigger the thyristor. So I have given a gate pulse at an angle of alpha is going to lie between theta to pi minus theta. So therefore, but from 0 to theta what you are going to get, from 0 to theta we can say that the source current is lesser than the E value. So therefore this thyristor will be in reversed bias. So this thyristor will be in reversed bias means simply we can say that negative voltage is going to occur across the thyristor. So therefore we are going to get a negative voltage across the thyristor, means it is an open circuit. So therefore the output voltage is equal to the value of E up to theta, whereas the load current is equal to 0 up to theta. Whereas from theta to alpha, Vs is greater than E, but we have not given the triggering pulse. So therefore it will be in the forward blocking mode. So therefore Vt of t will be positive, but it will be forward blocking mode, means simply we can say Vt of t is equal to Vs minus E, but still it is going to act like open circuit. So therefore still V0 of t is equal to E, and the current will be equal to 0 from theta to alpha. But from alpha to pi minus theta, the source voltage is greater than E. So therefore simply we can say that here now it is going to act like a, means the thyristor is going to act like a on circuit, so it is going to short circuit. So therefore the output voltage is equal to source voltage. So output voltage is equal to source voltage up to this region from alpha to pi minus theta. So therefore the output current is equal to source voltage minus E value by R. So we are going to get a value of current in this region. At pi minus theta, Vs of t is equal to E. So therefore the current will be equal to 0 at this range. But after that you can see clearly after pi minus theta, Vs of t is less than E. So therefore we can simply say that a reverse voltage is going to occur across the thyristor. So therefore it is going to act like an open circuit. So therefore the output voltage will be equal to the value of E, and the output current is equal to 0. So we are going to get, this is the graph we are going to get. So the current is non-zero only from alpha to pi minus theta. So now we are going to analyze the thyristor voltage. As I have already told you, from 0 to theta, from 0 to theta I have already told you that here Vs of t is less than A, it indicates that it is a negative voltage is going to get occur. A negative voltage is going to occur, which is equal to V2 of t is equal to Vs minus E at instant t is equal to 0, Vs is equal to 0, so 0 minus E is minus E, whereas at theta both are equal, so therefore difference value is equal to 0, so negative voltage is going to get occur from 0 to theta. Whereas from theta to alpha, I already told you here Vs is greater than E, so therefore it will be in the forward blocking mode, but still we have not given the triggering pulse. So because of that, it will be following the, means as it is an open circuit, then the voltage across the thyristor is equal to source voltage minus E. So therefore, this is the graph we are going to get. From alpha to pi minus theta, it was triggered, so it is conducting, so therefore its voltage is equal to 0. Whereas from pi minus theta onwards, after that again it will be in reverse bias because Vs is less than E, so therefore simply we can say that it is in reverse bias, means negative voltage is going to get appear, so therefore its voltage is equal to Vs of t minus E. So Vs of t minus E, so you can go plot this diagram. At this instant the peak value is minus Vm, so minus Vm minus E is nothing but minus of Vm plus E, so therefore the peak inverse voltage across the thyristor is equal to Vm plus E we are going to get. So therefore simply we can say this is the voltage we are going to get finally, the peak inverse voltage is equal to Vm plus E. So you can see clearly from pi minus theta to 2 pi, the thyristor is going to experience a negative voltage. Again from 0 to theta also it is going to experience a negative voltage. So overall angle is, this is pi to 2 pi is pi and this is theta. So pi plus theta, which is pi plus 2 theta. So for pi plus 2 theta, it is going to experience a negative voltage. So circuit turn of time is equal to pi plus 2 theta by omega. And the peak inverse voltage is equal to Vm plus E. So now we are going to analyze this circuit. As the source voltage is equal to Vm sin omega t, and I want to find what is the, at angle of theta, the source voltage is equal to E. So E is equal to Vm sin theta. So theta is equal to sin inverse of E by Vm. See, always the thyristor must be triggered for alpha greater than or equal to theta, means the range of alpha should be always from theta to pi minus theta only. In this region only the thyristor voltage is positive, then only we are going to then only we can apply the positive gate triggering pulse. So from 0 to theta, I have already told you the source voltage is less than E value, so therefore negative voltage is going to apply across the thyristor, so it will be reverse bias. So therefore thyristor is in the reverse bias, so it is going to act like open circuit. So therefore the output voltage is equal to value of E and the output current is equal to 0. From theta to alpha, we can simply say that from theta to alpha, as we are not given any triggering pulse, but it will be in a, as Vs of t is greater than E, but we are not given a triggering pulse, so therefore it is going to act like in a forward blocking mode. So as Ig is equal to 0, gate is not triggered, so it will be in the forward blocking mode, so therefore it is like an open circuit. So V naught of t is equal to E and I naught of t is equal to 0. From alpha to pi minus theta, it was triggered, so therefore thyristor is triggered, so therefore it is going to become like a short circuit. So output voltage is equal to source voltage and output current is equal to output voltage minus E by R, but output voltage is equal to source voltage, which is Vm sin theta minus E by R. Again from pi minus theta to pi, here the source voltage is less than E value, so therefore we can say that a negative voltage is going to apply across the thyristor, so therefore it is reverse bias, means it is going to act like open circuit, so therefore the output voltage is equal to value of E and the output current is equal to 0. And from pi to 2 pi also, still the source voltage is less than E, so therefore we can say still a negative voltage applied across the thyristor, so it will be in reverse bias, so therefore the output voltage is equal to E and the output current is equal to 0. So this is what we are going to analyze. And the circuit turn of time, I have already told you the whole angle is pi plus 2 theta. Only for pi plus 2 theta only we are going to get a negative voltage across the thyristor, which is 2 pi minus of pi minus theta plus theta by omega is equal to pi plus 2 theta by omega. So I have already told you for a range of pi plus 2 theta we are going to get a negative voltage, means if you want the circuit turn off time, the time for which the negative voltage applied across thyristor is equal to pi plus 2 theta by omega. So therefore now, if you want to know what is the source voltage RMS value, which is Vm by root 2, and if you want to know what is the average value of the output voltage, average value of the output voltage is equal to 1 by 2 pi integration of 0 to alpha e into d theta plus alpha to pi minus theta. For alpha to pi minus theta, it is equal to source voltage, which is Vm sin theta into d theta plus again pi minus theta to 2 pi, it is again e into d theta. So if you solve this one, we are going to get 1 by 2 pi into Vm into cos theta plus cos alpha plus e into pi plus theta plus alpha. So you are going to get this complex expression. So if you want to know what is the I naught average, because V naught average is equal to I naught average into R plus E, so therefore V naught average is equal to, so we can simply say I naught average is equal to V naught average minus E by R. So if you know V naught average, you can simply substitute this expression to figure out the value of the I naught average. So now gamma T, so the conduction angle of the thyristor is equal to, the conduction of the thyristor means the thyristor is going to conduct only from alpha to pi minus theta. So therefore pi minus theta minus alpha is equal to pi minus of theta plus alpha. Only for this range of angle, the thyristor is going to become conductive. So I naught RMS is equal to, so if you want to find what is the RMS value of the output current, is equal to under root over 1 by 2 pi integration of alpha to pi minus theta I naught of t whole square into dt. So if you solve this one, we are going to get finally 1 by 2 pi r square into Vs square plus E square into pi minus theta minus alpha plus Vs square by r into sin 2 theta plus 2 alpha minus 2 EVM cos theta plus cos alpha over the power of 1 by 2 we are going to get. So this is the complex expression, no need to remember. You can even easily figure out this value also. So now we are going to study the RLE load. So just we are going to keep an extra inductive in the previous circuit. So we are going to get RLE load. So for this RLE load, now we are going to analyze each and everything. So source voltage is plus or minus Vs of t, and the source current is Is of t, and the load current is I naught of t, and this is the RLE load. So the output voltage is plus or minus V naught of t. This is the direction of the source current. So now we are going to analyze this circuit. So now here, this is the source voltage. So Vm sin omega t, so we are going to draw this Vm sin omega t, and the value of E is always less than Vm, we are going to analyze. Then only it is a possible, then only we can trigger the thyristor. Otherwise, we are always, if V E is greater than Vm means the thyristor will be always in the negative or reverse bias. So here always it will be in reverse bias. That is the reason we are going to keep the value of E lesser than the Vm. So now here theta is equal to sine inverse of E by Vm. If this is theta, this is also pi minus theta. So now here simply we can say that this is the value of theta. So now the alpha is the triggering angle. Triggering angle of the thyristor is going to lie between the theta to pi minus theta. From theta to pi minus theta, we are going to lie the triggering angle of the thyristor. So now what we are going to do is basically at angle alpha, we are going to give a positive gate pulse to the thyristor. This triggering pulse we are going to give. So therefore simply we can say that here, now as we are going to give the triggering pulse from 0 to theta, I can say that Vs is less than E. So therefore simply we can say that it will be reverse bias. So therefore we can simply say it is reverse bias means open circuit. So output voltage is equal to value of E, and the output current is equal to 0. We are going to get like that. From theta to pi, from theta to alpha, even though Vs is greater than E, but we are not given the triggering pulse, so therefore it will be in the forward blocking mode. So therefore it is going to still act like open circuit. So therefore the output voltage is equal to still E, and the output current is equal to 0. Whereas from alpha, as you given the triggering pulse, so it is going to become like a short circuit, means it is going to become on position. So output voltage is equal to source voltage, and the current is going to get increased, means it will be increasing. So it will be increasing up to pi minus theta, it will be increasing. After that, what is going to happen is here, because now after that the current is going to get decay, because a current in an inductor cannot change instantaneously. So therefore it is going to become decay, because a negative voltage of the source voltage is going to apply. So because of that the current is going to get decay. So it is going to get decay, and finally it is going to become 0 at an angle of beta. So therefore after that what is going to happen is the current is going to become 0. So therefore from alpha to beta, now the thyristor is going to get conduct. The thyristor is going to get conduct. So therefore, output voltage is equal to source voltage up to alpha to beta. So up to alpha to beta, we have to draw the same source voltage we are going to draw. So after that, the current is equal to 0. So as the current is equal to 0 means simply we can say that it is an open circuit. So therefore, the output voltage is equal to value of E. So we are going to get like this. A current in an inductor cannot change instantaneously. So therefore, it will be charging and then discharging. So because of this phenomena, it will be always equal to source voltage from alpha to beta. So we can say that from alpha to beta only, the thyristor is going to get conduct. Again from beta to 2 pi, it is reverse bias because of negative voltage. So it is reverse bias means open circuit. So it will be equal to output voltage is equal to value of E and the output current is equal to 0. So now let me analyze the thyristor voltage. As I have already told you, from 0 to theta, the source voltage is less than E. So therefore, it is a reverse bias. So therefore, the thyristor voltage is equal to Vs of t minus E. So therefore, simply at t is equal to 0, we are going to get E Vs is equal to 0. So 0 minus E is minus E. At theta, both are equal. So therefore, it will become 0. Again from theta to alpha means a negative voltage is applied across the thyristor. Whereas from theta to alpha, the thyristor voltage means Vs of t is greater than E, but still we are not given a triggering pulse, so it will be in the forward blocking mode. So therefore, simply we can say that here it will be in the forward blocking mode means V2 of t is equal to Vs of t minus E. So therefore, it will be in a positive way we are going to get. From alpha to beta, the thyristor was conducting. So because of that, what is going to happen? Its voltage is equal to 0. Again from beta to 2 pi, from beta to 2 pi, a negative voltage is applied across the thyristor. So because of that, it will be in reverse bias. So therefore, simply we can say Vt of t is equal to Vs minus Vs of t minus E. So we are going to get in this fashion. So at this peak value, Vs is equal to minus Vm. So minus Vm minus E is equal to minus of Vm plus E. So this is the peak inverse voltage across the thyristor, which is Vm plus E. So this is the graph we are going to get. So simply a negative voltage is occurred across the thyristor from the region of 2 pi minus beta plus theta. For this region, the thyristor is going to experience a negative voltage which is 2 pi minus beta plus theta. So therefore, circuit turnover time is equal to 2 pi minus beta plus theta by omega, and the peak inverse voltage of the thyristor is equal to Vm plus E. So a current in an inductor cannot change instantaneously. So it will be charging and then discharging because of the negative supply voltage. So it will be discharging. So because of this only, for extra region, the source voltage is equal to load voltage from alpha to beta. So now we can get the output voltage expression and the input voltage means output voltage average value, output voltage RMS value we can figure out. By using that formula, we can get the I0 average and I0 RMS also we can figure out. So we know the value of TC and we know the value of peak inverse voltage. So all these things we can easily get from these diagrams. So now we are going to analyze another circuit which is RLA, the freewheeling diode. So only thing is from the previous circuit we are going to keep an extra freewheeling diode and everything is same. So now we are going to analyze this circuit. This is the source voltage Vs of t and this is the main thyristor and this is the Vt of t and this is the load of RLE load, and here output voltage is V0 of t and the output current is I0 of t, and this is the freewheeling diode. The current in the freewheeling diode is IFWD. I am going to assume a large amount of inductive current means a current will be always constant, because if the L is very large means current won't change, it will be always constant. So I am going to assume that L is equal to large means current will always remain constant. So now we are going to analyze this circuit. So now you can see clearly the source voltage is equal to Vs sin omega t. So this is the graph we are going to get, and here V0 of t. So see, you can see clearly here E value is always less than Vm. So therefore we are going to draw the value of E. So this is the angle theta and this is pi minus theta. So theta is equal to sin inverse of E by Vm. So alpha can be only from theta to pi minus theta. Only for this range only we can say that we can go for the triggering, because only in this range only the thyristor voltage is always positive. So therefore only in this range we can go for the triggering of the pulse or triggering of the thyristor. So therefore the range of alpha is only from 0 theta to pi minus theta. And also here simply we can say that suppose at alpha I am going to give the triggering. As I have already told you, the load current is always constant, so it will be always constant. Let me assume the I0 of t, the constant value is equal to I average. So let me assume this is I average. It is a constant current. It is a constant current. So I0 of t is nothing but it's a constant current of I average. So because I have assumed that L is very large. So because of that, what is going to happen from 0 to theta, from 0 to theta, or simply we can say 0 to theta, as the source voltage is less than value of E, so we can say that the thyristor is in the reverse bias. As thyristor in the reverse bias, so therefore it is open circuit. So as it is open circuit, so simply we can say that as it is open circuit, so therefore here RLE means, simply we can say as it open circuit means, simply we can say it is open circuit means we have removed it. So because of that, there is a V0. So V0 is going to become 0. Why? Means because here, because the load current is always positive, it is always non-zero. So therefore freewheeling diode is going to get conduct. So because of that, what is going to happen? V0 is equal to 0. So from 0 to theta, from 0 to theta, the freewheeling diode is going to get conduct. So therefore here the freewheeling current is going to get present, which is I average. Again from theta to alpha, Vs of t is greater than E, but still we are not given the triggering, so therefore it is going to act like open. So it is again open, but I0 cannot be equal to 0, means I0 is not equal, I0 is never 0, so it is a non-zero value. So because of that, again V0 is equal to 0. So therefore the freewheeling diode is going to conduct. So therefore again the freewheeling diode we are going to get a kind of I0 average. So from 0 to alpha, the freewheeling diode is going to get conduct. So because of that, we are going to get in this manner. From alpha we have given a triggering. So from alpha we have given a triggering. So therefore it is going to become the load voltage is equal to source voltage, because the thyristor was on. So therefore freewheeling diode will be off now, because Vs of t is positive. So because of that, the freewheeling diode was off. So therefore we are going to get a output voltage is equal to source voltage. So we are going to get in this format, we are going to get finally from alpha to pi. So therefore here the freewheeling means the thyristor is going to carry the current from alpha to pi. But here after that pi, what is going to happen is, again see, after that pi, what is going to happen is the current is always constant, the current is always constant. So now a reverse voltage means a negative voltage. So a negative voltage is going to get occur across the thyristor in this region, so it will be open circuit. Then again the freewheeling diode is going to get conduct. So because of that, the source the output voltage is equal to 0. So from pi to 2 pi, the output voltage is equal to 0. So we are going to get like this, means the freewheeling diode is going to get conduct from pi to 2 pi. So simply we can say that from alpha to pi, from alpha to pi, from alpha to pi, here simply we can say that the thyristor, main thyristor is going to get conduct, and from 0 to alpha and pi to 2 pi, here we are going to conduct the freewheeling diode. But in the previous case, the voltage is negative, but the negative voltage cannot appear because here the freewheeling diode is going to get conduct. So because of that only, here from alpha to 2 pi, the freewheeling diode was conducting. But in the initial case, the voltage was negative because there is no freewheeling diode. But here, because of freewheeling diode only, voltage cannot be negative. So therefore the freewheeling diode is going to get conduct. So therefore simply we can say that from pi to 2 pi, the freewheeling diode is conducting. Again from 0 to alpha, the freewheeling diode is going to get conduct. Only from alpha to pi, the main thyristor is going to get conduct. So this is the average, this is the output voltage we are going to get. So alpha to pi, we are going to get a freewheeling diode current, and 0 to alpha we are going to get a freewheeling diode current. Whereas only from alpha to pi we are going to get a thyristor current, and this is called as the loop current. So now we are going to analyze this circuit. So if you want to know what is the average value of the output voltage, the general expression is Vm by 2 pi into cos alpha minus cos beta. Here beta is equal to pi. So if you substitute here, we are going to get Vm by 2 pi into 1 plus cos alpha. And if you want to find what is the V0 average is equal to I0 average into R place, here VL average plus E, but VL average is equal to 0 because the inductor voltage is equal to average value is equal to 0. So therefore finally V0 average is equal to I0 average into R plus E. So whereas theta is equal to sin inverse of E by Vm, and Tc is the circuit turn of time. The circuit turn of time is the time for which the reverse voltage appear across the thyristor, main thyristor. See, from simply we can say that the freewheeling diode was conducting in this region from 0 to alpha. The freewheeling diode is conducting means we are going to experience a positive voltage across the thyristor. From here it is already conducting. From pi to 2 pi only, the freewheeling means only from pi to 2 pi only, the thyristor was experiencing a negative voltage because here the source voltage was negative. So because of that only we can say that here see, simply thyristor voltage is equal to source voltage minus load voltage. Here load voltage is equal to 0 here. So therefore Vt of t is equal to Vs of t. So Vd of t is equal to Vs of t means positive pulse we are going to get occur in this case. But from pi to 2 pi, the lead voltage is equal to 0. So therefore the thyristor voltage is equal to source voltage. Here the source voltage is negative. So therefore only negative pulse is going to get occur in this region like this. So finally if I draw the thyristor voltage, it will be like this. So this will be positive pulse, again 0, again negative we are going to get. So this is a positive, 0 and negative we are going to get. So this is the only for an angle of pi we are going to get a negative pulse. So pi by omega. So circuit turn of time is equal to pi by omega we are going to get. So thyristor voltage is equal to 0. So this is positive, 0 and negative. So therefore only for this region only we are going to get a negative voltage across the thyristor. So therefore the circuit turn of time is equal to pi by omega. So the conduction angle of the freewheeling diode is equal to pi plus alpha, whereas conduction angle of the thyristor is equal to pi minus alpha. So this is the analysis of this circuit. So now we are going to study about the midpoint type single phase full wave control rectifier. Midpoint type single phase full wave control rectifier. Single phase means we are going to give only one phase supply. Full wave means now we are going to get two pulses at the output of the signal, and we are going to basically rectify means converting AC to DC. So midpoint means basically we are going to use a center tap transformer for this one. So midpoint type single phase full wave control rectifier. So therefore the input is Vi of t. So this is for the primary of the transformer. So secondary we are going to tap into two parts. So this is plus or minus VAN and this is plus or minus VBN. So suppose let me assume this is plus or minus VAN and this is plus or minus VBN. So this is the control thyristor and this is also thyristor T1 and T2, and we are going to keep a load here. Let me assume the load resistor is R and this is plus or minus V0. Output voltage is plus or minus V0 and the output current is I0. So we can say this is single phase full wave center tap rectifier. Simply we can say that single phase full wave center tap rectifier. So therefore full wave means we are going to get two pulses at the output. Center tap transformer we are going to use. So basically the rectifier working is converting AC to DC. We are going to analyze the waveforms. So you can see clearly, see VAN and VBN are also sinusoidal waveforms, but only the phase difference is 180 degrees between them. So this is VAN and this is VBN. So therefore if VAN is positive, then VBN is negative. If VAN is negative, then VBN is positive. So therefore we are going to get VBN in this fashion. So now you can see clearly here, I am going to give a triggering for the thyristor T1. I am going to trigger at an angle of alpha. Similarly thyristor 3-2 I am going to trigger at an angle of pi plus alpha. So T1 is triggered at alpha, whereas T2 is triggered as pi plus alpha. So T1 is going to conduct only VAN is a positive. See, VAN is a positive only in this region from 0 to pi. So therefore the T1 is going to conduct only when VAN is a positive, means only alpha can vary from 0 to pi. Only in this range you can trigger the thyristor T1 because VAN is a positive. Whereas VBN, when the VBN is a positive, then only we can trigger the thyristor T2. So therefore VBN is positive only in this region. So we can say that we can trigger T2 only in this range. So that is the reason we are going to trigger the T1 in the range from 0 to pi, and then T2 we are going to trigger in the range from pi to 2 pi. So if you are going to trigger the T1 in this region, then we are going to get so before that T1 we are not going to trigger the T1, so therefore we can say it is forward blocking mode. As it is the forward blocking mode, so therefore we can say that here it is open circuit. So therefore simply we can say is it is open circuit means here V0 is equal to 0. As V0 is equal to 0, then simply current is also equal to 0. So current is also equal to 0. Whereas at T1 we are going to trigger the T1, so therefore it is going to become short circuit or it is on. So therefore V0 is equal to VAN with the help of KVL. So therefore simply we can say that now here simply we are going to get in this format, which is here this is called as a, so it is going to follow the VAN voltage. So VAN voltage it is going to follow up to pi. So the current will be VM by, which is V0 by R. So therefore peak value is Vm by R we are going to get. So this is the output voltage graph and this is the output current graph we are going to get for this pure resistive load. And from pi to pi plus alpha, from pi to pi plus alpha, T1 is in reverse bias whereas T2 is in the forward blocking mode. Whereas T2 is in the forward blocking mode, so simply we can say that here now T2 it is forward blocking mode, simply we can say that now it is off. So therefore simply V0 is also equal to 0. So now after T2, see we are going to trigger the T2 at pi plus alpha. So as we are going to trigger the T2 at this instant, so therefore V0 will be equal to VBN. So at this instant V0 will be equal to VBN. So therefore whatever the voltage of the VBN will be equal to V0. So simply this we are going to get V0. So current is equal to V0 by R. So therefore we are going to get this is the value of the current. So you can see clearly there are two pulses in 2 pi. So therefore we can say this is called as a single phase full wave shunt tap rectifier. Means we are going to get two pulses in a 2 pi. So we are going to call this as the full wave. We draw the voltage diagrams for the thyristor T1 and the thyristor T2. See, for thyristor T1 I have already told you for 0 to alpha it is in forward blocking mode. So whatever the supply voltage is equal to is the voltage across the VN is equal to voltage across the T1. So we are going to get this is the voltage forward blocking mode. From alpha to pi I have already told you that thyristor T1 is on. So therefore we are going to get this short circuit. So means it is on, means it is a short circuit. From see after pi Vn is a negative. So therefore it will be always under the reverse bias. It will be always under the reverse bias condition. So therefore it will be like this. So these are the graphs we are going to get finally. So this is the graph we are going to get and the peak value we are going to get the peak inverse voltage across the thyristor T1 we are going to get, which is minus 2 Vm, or simply we can say 2 Vm is the peak inverse voltage across the thyristor T1, because at this instant we can see that see Vt1 is equal to Van minus V0. So Vt1 is equal to Van minus V0, as Vn is equal to minus Vm and also V0 is equal to, here we are going to get plus Vm. So therefore if you do the subtraction we are going to get finally minus 2 Vm. So minus 2 Vm is the reverse voltage across the thyristor T1. So therefore Vt1 is equal to Vn minus V0. At this point you can see clearly here V0 is equal to Vm and Vn is equal to minus Vm. So minus Vm is minus 2 Vm. So minus 2 Vm is the reverse voltage across the thyristor T1. So here simply we can say that from pi to 2 pi, this thyristor T1 is going to face a reverse voltage, or circuit turn off time of thyristor T1 is pi by omega, because 2 pi minus pi is pi by omega is the circuit turn off time of the thyristor T1. Similarly for thyristor T2, if you want to draw the voltage across the thyristor T2, you can see that simply here already thyristor T2 from pi to pi plus alpha, then VBN is a positive in this case. Whenever the VBN is a positive means it is under the forward blocking mode, then it will be always equal to the VB means the V2 means the voltage across thyristor T2 is equal to VBN. So simply we can say that now here it will be following the VBN. So after that it is going to get short circuit, or it is on. So therefore it is going to become 0 from pi plus alpha to 2 pi. Only in this region the thyristor T2 is going to get conduct. After that again from 0 to alpha means here from 0 to pi the VBN is negative. So therefore V22 will be always in the forward, I can say reverse blocking mode. So because of this we can say that simply it is going to follow in this one. So V22 is equal to VBN minus V0. At this instant VBN is minus Vm and the V0 is plus Vm. So therefore finally you are going to get minus 2 Vm. So therefore peak inverse voltage across the thyristor T2 at this instant is minus 2 Vm. So therefore we can say that the peak inverse voltage across the thyristor is equal to 2 Vm, where Vm is the voltage or maximum voltage of the VAN or the VBN. So listen carefully, here Vm is the peak voltage of the VAN or the VBN. We are going to assume both are equal. So Vm is the peak voltage of the VAN or the VBN. So now we are going to analyze this circuit. The analysis, which is here midpoint converter, is also called as M2 converter because of two pulses in output. So this midpoint converter is also called as M2 converter because of two pulses in output. As in the output there are two pulses, so therefore we can say that this midpoint converter is also called as the M2 converter because in the output there are two pulses. And I have already told you the ripple frequency is equal to the number of pulses into supply frequency. As the number of pulses in the output is 2, so therefore the ripple frequency is twice the supply frequency. So this ripple frequency means here the output frequency of the output current or the frequency of the output current or the frequency of the output voltage. So FR means ripple frequency or the output frequency is equal to the number of pulses into supply frequency. As the number of pulses in the output voltage or the output current is 2, so we can say that is twice the supply frequency. So output frequency means the frequency of the output voltage or the frequency of the output current is twice the supply frequency. And the peak inverse voltage of the thyristor, which is faced by the T1 and T2, which is 2 times of Vm, where Vm is the maximum voltage of the VAN or the VBN. And the conduction angle of the thyristor, the conduction angle of the thyristor T1 or T2 is only from pi minus alpha, or simply we can say only from alpha to pi T1 is going to get conduct, and from pi plus alpha to 2 pi T2 is going to get conduct. The range of the conduction of the T1 or T2 which is only pi minus alpha. So the conduction of the thyristor is always the pi minus alpha. For a circuit turn off time, I have already told you for T1 from pi to 2 pi it is facing the reverse voltage, whereas for T2 from 0 to pi it is going to face the reverse voltage. So therefore we can say pi by omega seconds is the circuit turn off time. Means for this much amount of time the thyristors are going to face a negative voltage or the reverse voltage. So if you want to find what is the average output voltage, which is equal to 1 by 2 pi into 2 times of integration of alpha to pi Vm sin theta d theta, because there are two pulses from alpha to pi and pi plus alpha to 2 pi and both are symmetry, so therefore you have to go for twice. So V naught average is equal to 1 by 2 pi into 2 of alpha to pi Vm sin theta d theta. So if you solve this one, we are going to get Vm by pi into 1 plus cos alpha. So therefore, see, the only way to remember this basic formula, which is Vm by 2 pi into cos alpha minus cos beta into 2, where here beta is equal to pi. So if you substitute here, we are going to get finally Vm by pi into 1 plus cos alpha, means it is twice the half wave signal, or it is twice the, means average output voltage of the full wave is twice the average output voltage of a half wave rectifier. So like this you need to remember. And alpha I have already told you, alpha can range only from 0 to pi. As output average current is equal to, see, I have already told you V naught average is equal to I naught average into R. So therefore I naught average is equal to V naught average by R. So but I have already told you V naught average, just now we have figured out. Then if you know the, you can substitute here, we are going to get Vm by pi R into 1 plus cos alpha. So if you know the what is the value of the V naught average, then we can easily figure out the average value of the output current. And if you want to find what is the RMS value of the output current, which is output voltage, which is equal to under root over 1 by 2 pi into 2 times of, see, under root over 1 by 2 pi into 2 times of integration of alpha to pi Vm sin theta whole square into d theta. So like this we have to do. So if this simplification, finally we are going to get V naught RMS is equal to Vm by under root over 2 pi into pi minus alpha plus sin 2 alpha by 2 under root. So V naught RMS is equal to Vm by under root over 2 pi into under root over pi minus alpha plus sin 2 alpha by 2. It's a very important formula that you need to remember. So V naught RMS is equal to Vm by under root over 2 pi into under root over pi minus alpha plus sin 2 alpha by 2. Where Fr is called as the ripple frequency and Fs is called as the supply frequency. I have already told you the ripple frequency is equal to number of ripples into supply frequency. Ripple frequency means basically output frequency, means the frequency in the output voltage or the frequency of the output current. And the number of pulses means the number of pulses which are present in the output voltage or the output current. And Fs is the frequency of the supply. So now we are going to study the bridge type single phase full wave control rectifier. Bridge type single phase full wave control rectifier. So previously we have studied the semi-tap transformer to get the full wave, but we are going to study now bridge type single phase full wave control rectifier. So this is called as a bridge, and input we are going to get we are going to give a AC, and output we are going to get a DC. So this is called as a bridge type single phase full wave control rectifier. So full wave means in the output we are going to get two pulses in a given time period, and single phase supply we are going to give. So rectifier is going to basically convert a AC to DC. So let me assume this is the supply voltage which is Vs of t, and we are going to consider the four thyristors T1, T2, T3 and T4. So this is plus or minus Vt1, plus or minus Vt2, plus or minus Vt3, plus or minus Vt4, and this is the load resistor R. So the output voltage across the load resistor which is plus or minus V naught of t, and the load current is I naught of t. Now we are going to analyze this circuit. So this is called as a source voltage. So you can see clearly this is the source voltage. So this is the source voltage which is having a peak value of Vm and minus Vm. So here we are going to trigger T1 and T2. We are going to trigger the T1 and T2 at an angle of 5. So T1 and T2 both thyristors are triggered at an angle of 5. And similarly the T3 and T4, this T3 and T4 we are going to trigger at an angle of pi plus alpha. So therefore T1, T2 we are going to trigger at alpha, whereas T3, T4 we are going to trigger at pi plus alpha. So here now when we are going to trigger this one, then what is the output voltage and the output current we are going to figure out. Output voltage and the output current. So therefore you can see clearly here from before alpha, T1 and T2 are not even triggered. So simply we can say that as the both are not triggered, means they are in the forward blocking mode. As they are in the forward blocking mode means then they are acting like open circuit. Then whatever the means output voltage is equal to 0. So therefore whatever the means the output voltage is equal to 0. So therefore output voltage is equal to 0. It indicates that output current is also equal to 0 in that case. So Vt1 and Vt2 are going to face the forward block, or we can say forward blocking voltage of half of the supply voltage, because let me assume both are having the same voltage drop. So therefore Vt1 is equal to Vt2 is equal to half of the supply voltage. So we are going to get in this format. From alpha to pi, as T1, T2 we are going to trigger, so they are going to become short circuit. So therefore whatever the output voltage is equal to source voltage, so therefore we are going to follow the source voltage from alpha to pi. So therefore output current is equal to output voltage by resistor. So we are going to get in this format, which is here with the peak value of Vm by R. So this is the output current and this is the output voltage. So in this period alpha to pi, both thyristors are already in the short circuit. So therefore the voltage drop is equal to 0. But from pi to pi plus alpha, we can simply say that now from pi to means from pi, this the T1 and T2 are going to face a reverse voltage. Means reverse bias. So definitely they will be in the reverse bias condition for all the time. So they are going to face always the reverse bias voltage from pi to pi plus alpha, whereas T3 and T4 are going to face a forward blocking voltage. So they are going to face a forward blocking voltage. So because of that, what is going to happen, as they are going to face the forward blocking voltage, then this voltage drops. So they will be open circuit. So therefore output voltage is equal to 0 and output current is equal to 0. Then their voltage drop will be half of the supply voltage. So they will be following the supply voltage, like half of the this positive voltage they are going to get. Then after that pi plus alpha, the T3 T4 are going to get triggered. Then what is going to happen, as they are triggered, definitely there will be a short circuit. So therefore they are going to act like a on. So therefore the output voltage is equal to minus of the supply voltage. So if you apply the KVL, we are going to get for this region, which is V naught of t is equal to minus Vs of t. So we are going to get V naught of t is equal to minus Vs of t. We are going to get for this range. Whereas for here, if you apply KVL, we are going to get V naught of t is equal to Vs of t. But for here, we are going to get V naught of t is equal to minus Vs of t. We are going to get in this case. So it will be negative of the supply voltage, means they will be reverse. So we are going to get in this format. So output voltage is equal to output current is equal to output voltage by resistor. So you are going to get in this format of the current. So you can see clearly in a given range of 2 pi there are 2 pulses. So that is the result is called as a 2 pulse converter. So now these are the voltages across the T1 and T2 and T3 and T4. So these are the voltages which we are going to get across the T1 and T2 and the T3 and T4. So here, as I have already told you, this T1 and T2 they are going to face forward blocking voltage from 0 to alpha and is equal to half of the supply voltage. So therefore now from alpha to pi they are already in triggering, means they are already on, so it's equal to 0. Whereas from alpha to 2 pi what they are going to face is basically they are going to face a reverse voltage. They are going to face a reverse voltage. So they will be from alpha to 5 plus alpha they are going to face in this manner, whereas from pi plus alpha to 2 pi, they are going to face a voltage which is equal to supply voltage, if you apply the KVL. Because at this condition both the T1 and T2 are off. So if you apply the KVL, then we can say clearly that, so from pi plus alpha to 2 pi, so VT1 is equal to VT2 is equal to Vs of t. So we are going to follow blindly the source voltage. If you apply the KVL, we are going to get blindly the source voltage. So therefore we are going to get a source voltage in this manner. So therefore the peak value of minus Vm means we can indicate that the peak inverse voltage of the T1 and T2 which is Vm. Whereas for this one I wanted to tell you pi plus alpha, they are going to face a forward blocking voltage which is half of the supply voltage. So therefore they will be in this format. Again from alpha plus to 2 pi they are triggered, so they will be short circuit, means they are going to on, so voltage drop across them is 0. Whereas from 0 to alpha, from 0 to pi they are going to face a reverse voltage, whereas in this region from alpha to pi they are going to face half of the supply voltage, means they are going to face basically supply voltage itself. So therefore minus Vm they are going to face. So if you see the diagram, we can get these diagrams easily. So we can say that the peak inverse voltage experienced by this thyristor T3, T4 and T1, T2 peak inverse voltage is only Vm, which is equal to supply voltage maximum value. Now we are going to do the analysis of this circuit from 0 to alpha. So from 0 to alpha, I have already told you here T1, T2, T3, T4, all the thyristors are off. And also here T1 and T2 are going to face a forward blocking voltage which is, so they are off. So therefore simply we can say half of the supply voltage which is Vm sin omega by 2 we are going to get. And VT3 and VT4 they are going to face a negative voltage of the supply voltage. If you apply the KVL, we are going to get minus Vm by 2 into sin omega t. So like this they are going to get. So therefore as they are open, so V naught of t is equal to 0 and I naught of t is equal to 0. So this is the way that the diagram we are going to get. Whereas from alpha to pi, T1 and T2 are on, whereas T3 and T4 are off because they are going to experience a negative voltage. So they are off. So therefore VT3 is equal to VT4 is equal to, if you apply the KVL, it is negative of the supply voltage. So minus Vm sin omega t. So this is the reason this VT3 and VT4 are going to experience a peak inverse voltage of Vm. And V2 and V2 are triggered. So therefore they are going to experience a voltage of 0. So output voltage is equal to source voltage. So therefore I naught of t is equal to V naught of t by R. So we are going to get Vm by R into sin omega t. So whereas from pi to pi plus alpha, whereas all the thyristors are off, because T1 and T2 are experiencing negative voltage and T3, T4 are experiencing a forward blocking voltage. So therefore all are off. So VT1 is equal to VT2 which is minus of Vm by 2 sin omega t, whereas VT3 is equal to VT4 is equal to half of the Vm sin omega t. They are going to face in this format. So and output voltage is equal to 0 and the output current is equal to 0 in this format. And the output, because all are off, so therefore everything is 0. Whereas pi plus alpha to 2 pi, see T1, T2 are off because they are experiencing negative voltage, whereas T3, T4 are going to experience positive voltage. So therefore they are already on and also they are triggered. So therefore VT1 is equal to VT2 is equal to minus Vm sin omega t. So VT1 is equal to VT2 is equal to minus Vm sin omega t. So because of this reason only, they are going to experience a voltage of peak inverse voltage of Vm, whereas VT3 and VT4 are on. So therefore they are going to experience a voltage of 0. So V naught of t is equal to the source negative of the source voltage. So finally we are going to get Vm sin omega t, and I naught of t is equal to Vm by R sin omega t. Or simply we can say V naught of t is equal to minus Vs of t. So if you do this one, we are going to get this one same. So V naught of t is equal to Vm sin omega t and I naught of t is equal to Vm by R sin omega t. So you are going to get these graphs. Now if you want to find what is the average output voltage, so V naught average is equal to 1 by 2 pi into 2 times of integration alpha to pi Vm sin theta d theta. So if you solve this one, we are going to get Vm by pi into 1 plus cos alpha. So this is the average output voltage we are going to get. By knowing this, we can figure out the average output current also. So V naught average is equal to I naught average into R. So therefore I naught average is equal to V naught average by R. So if we substitute here, we are going to get Vm by pi R into 1 plus cos alpha, or simply it is equal to V naught average by R. And V naught RMS is equal to, just now already told you, I naught over 1 by 2 pi into 2 times of integration of alpha to pi Vm sin theta whole square to d theta. So if we solve this one, we are going to get Vm by I naught over 2 pi into pi minus alpha plus sine 2 alpha by 2 under root means 1 by root 2. So therefore 1 by 2 we are going to get. So V dot RMS is equal to Vm by under root over 2 pi into under root over pi minus alpha plus sine 2 alpha by 2. And the circuit turn off time for each thyristor, because here they are going to means for 0 to alpha, for T1 and T2, for 0 to alpha they are going to face a forward blocking voltage. From alpha to pi they are going to face in the conduction mode, whereas from phi to 2 phi they are in the reverse blocking voltage. So therefore only from phi to 2 phi they are going to face a negative voltage. So therefore Tc is equal to 2 pi minus pi, which is pi by omega seconds. So this is the circuit turn off time of the T1, T2 and also T3 and T4. And whereas peak inverse voltage is Vm, whereas in the previous case the synthetic transformer the peak inverse voltage is 2 Vm, whereas here the peak inverse voltage is equal to Vm only. So when alpha is equal to 0, when alpha is equal to 0 means they are purely diode. When alpha is equal to 0 means all the thyristors we can replace by purely diode. So therefore now if you substitute this alpha is equal to 0 in the average value expression, the RMS value expression, then we are going to get V dot RH is equal to 2Vm by pi and V dot RMS is equal to Vm by root 2 we are going to get. So ripple factor is equal to under root over form factor whole square minus 1. Whereas form factor is equal to RMS value by average value whole square minus 1. So if we solve this one we are going to get 0.483 we are going to get. This is the ripple factor we are going to get. The ripple factor is equal to under root over form factor whole square minus 1 we are going to get the expression. So now we are going to learn about the single phase fully controlled rectifier or single phase fully controlled converter or single phase full bridge converter. So these are the different names for this circuit. See, whatever the circuits that you are seeing here, this has a different names, which is single phase full wave control rectifier. Single phase means single phase supply. Full wave means the output we are going to get 2 pulses, and the control means we are going to use thyristors. So rectifier means basically converting AC to DC. It is also called as single phase fully controlled converter. Single phase fully controlled converter means single phase supply. Fully means here we are going to get 2 pulses in the output. Control means here we are going to use the thyristors. It's a converter of the rectifier. Or single phase full bridge converter. So single phase means the single phase supply we are going to give full bridge. It is a full bridge. So output we are going to get 2 pulses, and it is basically a converter. So these are the different names for this circuit. It is single phase full wave controlled rectifier or single phase fully controlled converter or single phase full bridge converter. So these are the different names for this circuit. So let me assume for this circuit, so this is the source voltage Vs of t and this is the source current Is of t. So these are the 4 thyristors T1, T2, T3 and T4. So these are the 4 thyristors T1, T2, T3 and T4. So this is plus or minus Vt1, plus or minus Vt2, plus or minus Vt3 and plus or minus Vt4. So these are the voltages across the T1, T2, T3 and T4, and this is the load we are going to connect. So therefore the load current is I naught of t and the load voltage is V naught of t, and we are going to assume, the assume is here, we are going to assume the load has some inductance and it is very highly inductive. So it is a very huge current, means huge value of inductor. So therefore the current cannot changes. So it will be current will always the current is going to, we are going to assume it is a constant current, means the load current is always constant. That is the assumption we are going to assume, that the L value is very huge. So therefore the current I naught of t is always a constant value. So based on this, now we are going to analyze the each and every aspect of the graph. So this is the source voltage, which is Vs of t is equal to Vm sin omega t. So this is the graph we are going to get. From 0 to pi it is a positive and pi to 2 pi it is negative. So with the peak value of Vm and minus Vm. So now we are going to give the gate triggering pulses. So we are going to give the gate triggering pulses for T1 and T2 we are going to give at alpha, whereas T3 and T4 we are going to give the gate triggering at pi plus alpha. So because T1 and T2 can be given the positive triggering only when the source voltage is positive, only in this region they can give, whereas T3 and T4 they can be given only positive triggering only when Vs of t is negative. Only in this region we are going to give the triggering for the T3 and T4. So what is going to happen is, I have assumed that the load current is always constant, means it is always constant current. So based on that, here the output voltage we are going to draw. So as we are going to trigger T1 and T2 at alpha. So whenever this both are triggered at T1 and T2, then what is going to happen? As they are triggered, the load voltage is equal to source voltage. So from alpha to pi, whatever the source voltage is equal to load current, and here from alpha to pi, whatever the source voltage is equal to load voltage. And also from pi to pi plus alpha, see from pi to pi plus alpha, is T1, T3, T4 are not triggered, they are not even triggered, so they cannot be on. But T1 and T2 are going to on because the current is always constant. So current is always constant means it has to flow in the circuit. So definitely T1 and T2 are going to conduct even in this region also. So listen carefully. So therefore, as pi to pi plus alpha, T3 and T4 are in the forward blocking mode. They are not even triggered. But the current will be always positive means current is non-zero. So current will be only non-zero when T1 and T2 are still conducting. So therefore, from pi to pi plus alpha also, T1, T2 are going to get conduct. So whenever the T1, T2 are going to conduct, so the load voltage is equal to source voltage. So it will be again source voltage only. So from alpha to pi plus alpha, T1, T2 are going to trigger, are going to conduct. So therefore, the load voltage is equal to source voltage. Whereas from pi plus alpha to 2 pi plus alpha, we are going to trigger the T3, T4. As we are going to trigger the T3, T4, so therefore, if you apply the KVL, we are going to get. So if you apply the KVL, we are going to get V naught of t is equal to minus Vs of t. So it will be negative of the source voltage. So it will be negative graph. So we are going to get in this format. Similarly, from here 0 to alpha, everyone means T1, T2 are forward blocking mode, whereas T3, T4 are always conducting. Then only the current will continuous. So therefore, it will be again reverse of the supply voltage. So if it is a positive, it will be negative. So therefore, this is the graph we are going to get. So from alpha to pi plus alpha, T1, T2 are conducting, and from pi plus alpha to 2 pi plus alpha, T3, T4 are going to get conduct. So from alpha to pi plus alpha, V naught of t is equal to Vs of t, whereas from pi plus alpha to 2 pi plus alpha, V naught of t is equal to minus Vs of t. So this is the value we are going to get. So this is the output voltage graph we are going to get. So this is called as the, see, you can see in a given 2 pi there are 2 pulses. So 2 pulses are present. So therefore it is called as a full wave control rectifier. So now I want to draw what is the thyristor voltages T1 and T. I want to draw the thyristor voltage for the T1, T2 and T3, T4, and also output current. See, this is called as the output current and this is called as the source current. So this is the source current and this is the output current. As I already told you, the output current is always constant with respect to time. So the current is always constant because we have assumed that the L is very high. So based on this, we are going to go for the analysis of the thyristor voltages for each and everything we are going to study. So for the thyristor T1 and T2, we are going to study starting. So I have already told you from 0 to alpha, T1, T2 are the forward blocking mode, means they are open circuit. Means they are actually, so T1, T2 are not even triggered. So they are in the forward blocking mode, means they are in the open circuit. At this condition, T3 and T4 are conducting. So therefore we can say that there will be zero voltage across them. So now if you apply the KVL, we are going to get VT1 is equal to VT2 is equal to Vs of t we are going to get. So it will be Vs of t forward blocking mode. So whereas from alpha to pi plus alpha, I have already told you T1, T2 are going to conduct. So therefore there will be short circuit voltage or voltage across them is 0. Again from pi plus alpha to 2 pi, they are in the reverse blocking mode because the negative voltage is going to get occur. So therefore if you apply the KVL in this pi plus alpha to 2 pi, whereas in this region T3 and T4 are going to get conduct. So therefore now still we are going to get. Therefore here VT1 and VT2 we are going to get Vs of t. So therefore it will be negative. So therefore you can see clearly here only for pi plus alpha to 2 pi, the thyristor T1 and T2 are going to face a negative voltage. So therefore here circuit turnoff time will be 2 pi minus of pi plus alpha by omega, which is simply we are going to get pi minus alpha by omega is the circuit turnoff time of the T1, T2 and T3 and T4. If you want to apply for T3 and T4, here I already told you T3 and T4 are going to connect from 0 to alpha. So they are short circuit, means voltage across them is 0. Whereas from alpha to pi, we can say that T1 and T2 are, so from alpha to pi plus alpha, T1, T2 are going to triggered, or they are in the on position. So whenever they are on position, if you apply the KVL, then we are going to get Vt3 is equal to Vt4 is equal to minus of Vs of t. So minus of Vs of t we are going to get in this fashion. So therefore you can see minus of Vst we are going to get. So only for alpha to pi they are going to face a reverse voltage. So therefore we can say that the circuit turn off time is equal to pi minus alpha by omega. And from pi to pi plus alpha they are going to face a forward blocking voltage. And from pi plus alpha to 2 pi again they are in on position. So therefore the voltage across them is 0. So peak inverse voltage of T1, T2, T3, T4 is Vm. So you can see clearly Vm is the peak inverse voltage across the diode, across the thyristor T1, T2, T3 and T4. And now this is the load current is always constant. If you want to draw what is the source current, so if you want to draw the source current from alpha to pi plus alpha, T1 and T2 are in the conduction mode. So therefore if you apply the KCL we are going to get Is of t is equal to I naught of t. So whatever source current is equal to load current from alpha to pi plus alpha. Whereas from pi plus alpha to 2 pi plus alpha, the T3, T4 are going to get conduct. So therefore Is of t is equal to minus I naught of t. So therefore it will be negative of the load current. So therefore here minus I naught and minus I naught. So simply from alpha to pi plus alpha, the Is of t is equal to I naught of t. Whereas from pi plus alpha to 2 pi plus alpha, then Is of t is equal to minus I naught of t. So because of that it will be negative current. So therefore this is the current of the source current and this is the load current. So we can say this is a square wave. So this is in the format of a square wave. So this is in the format of a square wave. So the shape of the source current is always a square wave. So now with the help of these diagrams, now we are going to analyze this circuit. So now we are going to do the analysis with the assumption that it is a continuous conduction mode, means current is not at all zero, it is always a constant value, means it is always non-zero value. So that will, with the help of this assumption, now we are going to study this one. So assume that I naught is equal to constant for RLE and RL load. So we have assumed that basically the load is either RLE or RL load. Then only the current will be always constant, because we are assuming that L is a very huge load. So load can be either RLE load or RL load. So it will be always current is equal to constant, that we are going to assume here. And I have already told you from alpha to pi plus alpha, T1, T2 are on. So whenever the T1, T2 are on, so therefore the voltage across the T1 and T2 is equal to 0. So if you apply the KVL, which is Vt3 and Vt4, if you apply the KVL, then we are going to get, which is minus of Vst. So minus of Vst we are going to get, which is minus Vm sin omega t. So this is the expression we are going to get from alpha to pi plus alpha. So this is minus Vs of t. Whereas as now if you apply the KCL we are going to get, then the source current is equal to load current. So source current is equal to load current from alpha to pi plus alpha. Whereas from pi plus alpha to 2 pi plus alpha, T3, T4 are going to get on, whereas T1, T2 are off. So because of this, what is going to happen is, as T3, T4 are on and T1, T2 are off, so therefore Vt1 is equal to Vt2 is equal to minus Vs of t. So if you apply the KVL, we are going to get negative of the supply voltage. So this is positive of Vs of t. So positive of Vs of t means if you apply the KVL, the thyristor voltage across the T1 and T2 both are equal to the source voltage. So therefore from pi plus alpha to 2 pi plus alpha, so therefore they are going to blindly equal to the source voltage. So they are going to blindly follow the source voltage, which is plus Vs of t. So this is plus Vs of t. So if you apply the KCL, we are going to get, then Is of t we are going to get minus I naught. So this is the minus I naught we are going to get. So therefore if you want to know what is the average output voltage, which is here, simply we can say that here 1 by pi. So or simply we can say 1 by 2 pi into 1 by 2 pi into 2 times of alpha to pi plus alpha Vm sin theta d theta. So 1 by 2 pi into 2 times of alpha to pi plus alpha Vm sin theta d theta. So simply we are going to get 1 by pi into integration of alpha to pi plus alpha into Vm sin theta d theta. We are going to get 2 Vm by pi into cos alpha. So this is the expression we are going to get, which is 2 Vm by pi into cos alpha. So 2 Vm by pi into cos alpha is the expression that you are going to get. So 2 Vm by pi into cos alpha is the expression of the output average voltage we are going to get. So circuit turn of time, I already told you circuit turn of time, which is pi minus alpha by omega. So only for T1 and T2, they are going to face a reverse voltage only from pi plus alpha to 2 pi. So therefore, simply if it is subtraction of 2 pi minus of pi plus alpha, we are going to get pi minus alpha. So circuit turnover time is equal to pi minus alpha by omega. And conduction or the conduction angle of the thyristors. The thyristors are going to connect from T1 and T2 are going to connect from alpha to pi plus alpha. So if we do the difference of this, we are going to get pi plus alpha minus alpha is equal to pi. Whereas T3, T4 are going to connect from pi plus alpha to 2 pi plus alpha. So if we do the subtraction, we are going to get again pi. So therefore, the conduction angle of each thyristor in this case is equal to pi. And alpha can lie from 0 to 180 degree only. So this is the triggering angle. It can lie from 0 to 180 degree. So if alpha is equal to 0, and if you substitute in this average output voltage, we are going to get V average is equal to 2Vm by pi. So therefore, if you substitute and the conduction angle of thyristor is equal to pi. If you substitute alpha is equal to 90 degree in this expression, so cos 90 is 0. So therefore, V average is equal to 0, and the conduction angle is equal to phi. It is independent of the alpha. It is independent of the alpha. Whereas alpha is equal to 180 degree. So if you substitute alpha is equal to 180 degree, in this case, if you substitute alpha is equal to 180 degree, then cos 180 is minus 1. So therefore, V average is equal to minus 2Vm by pi. So output average voltage is equal to 2Vm by pi into cos alpha, whereas alpha can lie from 0 to 180 degree. So with the variation from 0, 90 and 180, so we are going to get in this format, which is 2Vm by pi, 0 and minus 2Vm by pi. So here, the gamma is in the conduction angle of thyristor is independent of alpha for up to here. Whereas at 180 degree, it is going to become 0, means they are not going to get conduct at all. So therefore, it is equal to 0. So from 0 to 90 degree, the average value is always positive, whereas from 90 to 180, the average value of the output voltage is negative. So now, I want to draw what is the thyristor current. Let me take the thyristor T1. So let me take the thyristor T1. Means what is the current to the thyristor I want to figure out. So let me assume the thyristor T1. So thyristor T1 is going to connect only from alpha to pi plus alpha. So therefore alpha to pi plus alpha it is on, and remaining unit time it is off. It is open circuit. So therefore from alpha to pi plus alpha it is on. So therefore current means whatever the load current is equal to the current to the thyristor T1. So therefore I naught of T is equal to means IT1 is equal to I naught. So therefore it will be I naught. So only from alpha to pi plus alpha. So now I want to find what is the thyristor average current, average value of thyristor current, which is I naught into the means first I want to find what is the area of this one. I naught into pi by 2 pi in a period of 2 pi. So you are going to get I naught by 2. If I want to find what is the RMS value of the thyristor current, which is I naught into under root over pi by 2 pi. So we are going to get I naught by root 2. This is I naught by root 2 we are going to get. Then the thyristor average value is equal to I naught by 2, and the thyristor RMS value is equal to I naught by root 2. Then if alpha is less than 90, if alpha is less than 90, I have already told you the average value of the output voltage is always positive or greater than 0, and I naught is always greater than 0. So therefore you can say that here rectifier power transfer from source to load. So if the product of these two things, the output power is always greater than 0. So therefore the load is absorbing the power from the source. So therefore it is going to act like a rectifier, means converting AC to DC. So when alpha is less than 90, the output average value is positive and the output average value current is also positive. So if the product of these two things, the average output power is again positive. So therefore we can say that it is going to act like a rectifier mode, means power is transferring from source to load. So therefore power is transferring from source to load. Whereas if alpha is greater than 90, then definitely we can say that output average value is always less than 0. If you substitute here alpha greater than 90, the average value is less than 0, whereas output average value current is always greater than 0. It is always constant. So if we do the product of these two things, then we can say it is a negative. So therefore power is transferring from load to source. So power is transferring from load to source means converting DC to AC. So it is acting like an inverter. Whereas in the first case it is converting AC to DC. So we can say that it is acting like a rectifier. Whereas in the second case it is converting DC to AC. So we can say it is acting like a inverter. In the first case it is converting AC to DC, means it is acting like a rectifier. In the second case it is converting DC to AC. So we can say it is acting like a inverter. So when alpha is less than 90, V dot is greater than 0 and I dot is also greater than 0. So the product is also greater than 0. So therefore means power is greater than 0 means the power is flowing from source to node. So therefore simply we can say that the power is transferring from source to node means it is going to act like a rectifier means converting AC to DC. Whereas in the second case when alpha is greater than 90, so therefore the average output voltage is less than 0 and the average output current is greater than 0. So if the product of these two things, then the average power is also less than 0. It indicates that power is transferring from load to source. It indicates that it is converting DC to AC. So it is acting like a inverter in this case. We are going to do the harmonic analysis of the IS of t. I already told you from pi to pi plus alpha, then I naught of t means IS of t is equal to I naught of t, whereas from pi plus alpha to 2 pi plus alpha, it is IS of t is equal to minus of the I naught of t, which is minus I naught. So we are going to get this graph we are going to get. So now we are going to do basically the harmonic analysis of this source current we are going to study. Source current, the expression of the source current is, so if you apply the Fourier series, because it is a periodic waveform, so if you apply the Fourier series, then we are going to get the expression of the source current, which is sigma n is equal to 135 up to infinity 4 I naught by n pi into sine of n omega naught t minus n alpha. I already told you this expression, which is Is of t is equal to sigma n is equal to 135 up to infinity 4 I naught by n pi into sine of n omega naught t minus n alpha. So this is the general expression I already told you, which is Is of t is equal to sigma n is equal to 135 up to infinity, which is 4 I naught by n pi into sine of n omega t or n omega naught t. You can go for anything, n omega naught t minus n alpha. So Is of t is equal to sigma n is equal to 135 up to infinity 4 I naught by n pi into sine of n omega naught t minus n alpha. So I want to find what is the fundamental component RMS value. Means the fundamental component RMS value of the source current, which is, if you want to know what is the fundamental component peak value, which is 4 I naught by pi, but if you want the RMS value, go for division by under root of 2. So therefore 4 I naught by pi by root 2. So if you solve this one, we are going to get 2 root 2 by I naught by pi, 2 into root 2 I naught by pi. This is the RMS value of the fundamental component of the source current. And if you want to find what is the overall source current RMS value, which is equal to I naught, so the overall source current RMS value is equal to I naught, whereas G is called as the distortion factor. It is the ratio of the RMS value of the fundamental component current by the overall RMS value. So we know the value of IS1 RMS and IS RMS. So do the division, we are going to get 2 into root 2 by pi. So 2 into root 2 by pi is called as the 0.9. So 0.9 is the distortion factor. It is a ratio of the RMS value of the fundamental source current by the RMS value of the overall source current. It is equal to 0.9 for this case. So I have already told you THD. THD is equal to under root over 1 by G whole square minus 1. So you know the value of G, substitute here, and if you solve this one, we are going to get 48.34%. So the distortion factor is equal to 0.9, whereas THD is equal to 48.34%, means this much amount of harmonics are going to present in the source current. So you can see clearly, irrespective of the alpha, we can say that G is equal to 0.9 and THD is equal to 48.34% we are going to get. Then I have already told you the average output voltage and the current I naught, average output current. Whereas from 0 to 90 degree, V naught average is positive and I naught is also positive. So this is the graph we are going to get in the first coordinate. So this is called as a rectifier, means we can say simply the power is transferring from source to load. So therefore it is going to act like a rectifier, means converting AC to DC. Whereas when the alpha is varying from 90 to 180, we can say that when alpha is varying from 90 to 180, we can say simply that V naught is negative. So V naught is negative, whereas I naught is positive. So therefore if you do the product, the power is negative, means the power is transferring from load to source, means we are converting DC to AC. It is called as the inverter or the regenerative mode. It is also called as inverter mode or the regenerative mode. So therefore this is the meaning of this graph. So this full wave can do work in two coordinates, which is first coordinate and the fourth coordinate. So it is basically this circuit can do working in first coordinate and also in the fourth coordinate. Here it is positive or negative, but the current is always positive. And the input power factor is equal to distortion factor into fundamental displacement factor. So therefore input power factor is equal to distortion factor into fundamental displacement factor. So now here input power factor is equal to G value we know, which is 0.9, and now fundamental displacement factor is equal to cos of angle between the source voltage and the fundamental component of the source current. So you can see clearly here. Here you can see clearly the source voltage is equal to Vm sin omega t, whereas the fundamental component of the source current, which is equal to I, or simply we can see that 4 I naught by pi into sine of omega naught t minus alpha. So you can see clearly the alpha is the angle, phase angle between the alpha is the phase angle between the source current, source voltage and the fundamental component of the source current. So therefore we can say cos of alpha. So fundamental displacement factor is equal to cos of angle between the source voltage and the fundamental component of the source current, which is cos of alpha. So you can go for the multiplication of these two things. We are going to get input power factor is equal to 0.9 cos alpha, because it is a lagging, because we are going to use the inductors. So always it will be always lagging, means the source current is going to lag the source voltage. So input power factor is equal to 0.9 cos alpha. So 0.9 cos alpha. So therefore here you can see, you can go in another fashion also to get the value of cos phi. Cos phi is called as the input power factor, which is here input power is equal to output power. Input power is Vs RMS into Is RMS into cos phi is equal to output power is equal to. So output, and we can say input power is equal to, we can go for the fundamental component power also, which is Vs into Is1 into cos alpha. So this is called as the, simply this is Vs RMS into Is RMS into cos phi is equal to Vs RMS into Is1 RMS into cos alpha. So these both are going to get cancelled. Then we can say input power factor is equal to Is1 by Is is called as the, this is called as distortion factor. Here we are going to get 0.9 and this is cos alpha. So input power factor is equal to 0.9 cos alpha. So 0.9 is called as distortion factor, and alpha, cos alpha is called as the fundamental displacement factor. So we can get this expression in another format also. I have already told you input power is always equal to output power, because the losses in the devices we are going to assume at 0. So therefore Vs RMS into Is RMS is equal to cos phi is equal to output power we are going to assume, which is V naught average into I naught average. Whereas Vs RMS into Is RMS into cos phi is equal to V naught average, I have already told you, which is 2Vm by pi into cos alpha into I naught average value. The average value of the output current is always equal to I naught, because the average value of the output current is equal to I naught, and the RMS value of the output current is always equal to I naught, whereas the RMS value of the supply current is equal to I naught. So therefore these two are going to get cancels. So therefore input power factor is equal to 2Vm by pi cos alpha by here RMS value of the supply voltage is Vm by root 2. So if you solve this one, we are going to get finally 0.9 cos alpha. So therefore input power factor is equal to 0.9 cos alpha. We are going to get from this expression also, which is Pin is equal to P output, which is Vs RMS into Is RMS into cos phi is equal to V naught average into I naught average. So I naught average is equal to I naught and Is RMS is equal to I naught. They both are going to get cancelled, and if the simplification, and Vs RMS is Vm by root 2. So if you solve this one, we are going to get input power factor is equal to 0.9 into cos alpha, or the single phase full wave control rectifier. And input power factor is also called as the, see, IPF is also called as the input power factor or the supply power factor. It is a cause of phase angle between the supply voltage and the supply current. Whereas fundamental FDF is also called as the fundamental displacement factor. FDF means fundamental displacement factor. If alpha is equal to 0, we get all parameters for single phase full wave uncontrolled rectifier. So if you substitute alpha is equal to 0, this whole thing we are going to converge in terms of diodes, means single phase full wave uncontrolled rectifier, or simply we are going to call it as a single phase full wave uncontrolled bridge rectifier. So this is going to convert into a bridge rectifier, means all the things are going to convert in terms of a diodes. So if alpha is equal to 0, we get all parameters for single phase full wave bridge uncontrolled rectifier. Then here, if suppose I already told you alpha is going to change from 0 to pi. So alpha is going to change from 0 to pi, and what RMS is equal to. So if you want to find what is the RMS value of the output voltage, it is equal to Vm by root 2. So the output RMS value, the output voltage RMS value is equal to Vm by root 2. It is Vm by root 2. And if you want to know what is the fundamental, means the frequency of the fundamental component of the output voltage, which is, because we can write in terms, as it's a periodic signal, we can write in terms of the Fourier series, but I want only what is the fundamental frequency component of the output voltage because it is going to have two pulses in the output signal. So therefore it is twice the supply frequency or the supply input frequency. So therefore the frequency of the fundamental component of the output voltage is equal to twice the supply frequency, which is the FH is called as the supply voltage frequency. So the frequency of the fundamental component of the output voltage is equal to twice the supply frequency. So now we are going to analyze the single phase full wave semi-converter. So now we are going to analyze the single phase full wave semi-converter, or it is also called as the single phase off controlled converter, or it is also called as the single phase semi-converter off controlled single phase bridge rectifier. So these are the different names for this circuit. So single phase full wave semi-converter. So single phase supply we are going to give, and in the output we are going to get two pulses. So this is called as a full wave, and semi-converter means we are going to use both the thyristors and also diodes. Or it is also called as the single phase off control converter. So single phase supply off control means here we are going to use some as thyristors and some as diodes, and also it is a converter or the rectifier. Or single phase semi-converter means it's a combination of both thyristors and also diodes. Or it is also called as the off control single phase bridge rectifier. Off control means here we are going to use basically thyristors and the diodes. So that is the reason we are going to call it as the off control single phase bridge rectifier. So this looks like a bridge. That is the reason it is called as a single phase bridge rectifier. So this is the supply voltage. So this is the supply voltage we are going to get. So this is the supply voltage, which is Vs of t is equal to Vm sin omega t. So from 0 to pi it is a positive pulse, and from pi to 2 pi it is a negative pulse. Peak value of plus Vm and minus Vm. So here we are going to do the triggering for the thyristor T1 and T2. So T1 we are going to trigger at alpha, whereas T2 we are going to trigger at pi plus alpha, because T1 we can only trigger in the positive pulse of the voltage, whereas T2 we can trigger only in the negative pulse of the voltage. So because of this reason only T1 is triggered as alpha and T2 is triggered at pi plus alpha. So now at alpha now we are going to find what is the output voltage of the circuit. See, at alpha we are going to trigger the T1. So if you are going to trigger the T1, then definitely D2 is also going to get conduct. So therefore D2 is going to get conduct. So therefore we can say that T1 and D2 are going to conduct from alpha to pi. So T1 and D2 are going to conduct up to alpha to pi. So therefore we can say that if in this region alpha to pi T1 and D2 are on, so therefore whatever the output voltage is equal to the source voltage. So therefore V naught of t is equal to Vs of t. So the output voltage is going to follow the source voltage. And also in this region, by applying the KCL, we can say that Is of t is equal to I naught of t. I have already assumed the load is always having a constant current. So the load is going to have a constant current all the time. So I naught. So therefore here Is of t is equal to I naught. So therefore whatever the source current from alpha to pi is equal to I naught. So therefore this is the value of the source current I naught. Whereas from pi to pi plus alpha, I can say that simply from pi to pi plus alpha we can see clearly, which is that thyristor T2 is not triggered. So therefore it will be in the forward blocking mode. So therefore here, but the current should be continuous. So therefore we can say that T1, D3 are going to conduct. Only this is the low resistance path for the current to flow. So therefore T1, D3 are going to conduct. So T1, D3 are going to conduct. So therefore the output voltage will be is equal to 0. The output voltage is equal to 0. So therefore this is we are going to get 0. In this region the source current will be equal to 0. So therefore the source current is equal to 0 in this region. Whereas at pi plus alpha we are going to trigger the T2. So therefore T2 is going to get on. So therefore now as the T2 is going to get on, so therefore T3 is also going to get on default. So therefore T2, D3 are going to get conduct. So therefore if you apply the KVL, then we are going to get V naught of t is equal to minus Vs of t. So it is negative of the Vs of t. So we are going to get this graph. So from pi plus alpha to 2 pi, T2, D3 are going to conduct. So therefore, and if you apply the KCL, we are going to get in this region I Is of t is equal to minus I naught of t. So therefore you can say it is minus I naught. So therefore this is the value we are going to get. Whereas from 0 to alpha, from 0 to alpha T1 is in still forward blocking mode. So therefore definitely T2 and D2 are going to conduct even in this field also. So T2, D2 are going to conduct. So therefore the output voltage is equal to 0 and the source current is also equal to 0. So this is the diagram we are going to get for the output voltage and also source current. So this is the source current we are going to get. And if you want to know what is the thyristor current, so let me assume the thyristor T1. I want to draw what is the current in the thyristor T1. As you can see clearly, T1 is going to conduct only from alpha to pi plus alpha. Only from alpha to pi plus alpha, T1 is going to get conduct. So therefore, whatever the current in the thyristor, it is equal to the load current. So therefore, it is going to flow through this load current. So therefore, simply we can say from alpha to pi plus alpha, the thyristor T1 is going to conduct, and in the remaining regions it is not at all conducting. So it is open circuit. So current is 0 in the remaining range. Whereas from alpha to pi plus alpha, T1 is going to get conduct. So therefore, whatever the thyristor current T1 is equal to load current I naught. So therefore, this is the value of the current in the thyristor T1 we are going to get. So now I want to draw what is the current in the diode. Let me assume I want to find what is the current in the diode D2. As you can see clearly, D2 is going to conduct from 0 to pi. So D2 is conducting from 0 to pi. So 0 to pi, D2 is conducting, and in the remaining regions, D2 is not conducting, means it's open circuit. So current through the diode D2 is 0 in this range. Whereas in this range, the current through the diode is equal to the load current. So therefore, it is also equal to I naught. So only from 0 to pi, D2 is conducting, which is equal to load current. So this is the I naught. So we have drawn the current through the thyristor and also current through the diode. And I have already told you, we have assumed that the load current is a constant value because we have assumed that the load is either RLE load or RL load. So therefore, the inductance is going to have a huge value. So therefore, there is no change of the current I naught. So it will be always constant with respect to time. So this is the value of the current I naught of t. So now we are going to do some more analysis of the circuit. See, I have already told you here. You can clearly see that the conduction angle of the thyristor is equal to the conduction angle of the diode is equal to pi. Because you can see clearly from this diagram, say T1 is going to conduct from alpha to pi plus alpha. So T1 is going to conduct from alpha to pi plus alpha. So therefore, pi plus alpha minus alpha is equal to pi. So therefore, the conduction angle of the thyristor is equal to pi. And similarly, D2 is conducting from 0 to pi. So therefore, we can say that D2 is also conducting for a range of pi. So therefore, each thyristor and each diode are going to conduct for an angle of pi. So therefore, the conduction angle of the thyristor is equal to the conduction angle of the diode is equal to pi in this symmetrical circuit. So now, if you want to know what is the circuit turn of time, means the time for which the reverse voltage occurred across the thyristor T1. If you want to figure out, I have already told you here, thyristor T1 is conducting from alpha to pi plus alpha. So whereas from 0 to alpha, the thyristor T1 is going to face a forward blocking voltage. Whereas from alpha to pi plus alpha, it is conducting, and from pi plus alpha to 2 pi, it is going to face a reverse voltage, means it is under the reverse bias. So therefore, see, only from pi plus alpha to 2 pi, it is going to have a reverse voltage across the thyristor. So circuit turn of time is equal to 2 pi minus of pi plus alpha by omega. So if you solve this one, we are going to get pi minus alpha by omega. So this is the time for which the reverse voltage is going to occur across the thyristor T1. And if you want to know what is the average value of the thyristor current, then here I have already told you the current in the thyristor T1 is flowing from alpha to pi plus alpha. So therefore, IT average is equal to I naught into pi by 2 pi. So we are going to get I naught by 2. Whereas the RMS value of the current in the thyristor is equal to I naught into under root over pi by 2 pi, which is I naught by root 2 we are going to get. Similarly, the average value of the current in the diode, as in the diode D2, the current is flowing from 0 to pi. So therefore, simply we can say that I naught into pi by 2 pi, which you are going to get I naught by 2, whereas ID, the RMS value of the diode current is equal to I naught into under root over pi by 2 pi, we are going to get I naught by root 2. So this is the analysis of this one. So you can see clearly for this symmetrical circuit, the conduction angle of the thyristor is equal to the conduction angle of the diode is equal to pi. Whereas the RT means the average value of the thyristor current is equal to the average value of the diode current is equal to I naught by 2, whereas the thyristor current RMS value is equal to the diode current RMS value is equal to I naught by root 2. So some more analysis now we are going to do for the symmetrical circuit. I have already told you from alpha to pi, T1 and D2 are going to get on. As T1 and D2 are going to get on, so therefore whatever the output voltage is equal to source voltage if you apply the KVL, and also the source current is equal to the load current which is I0. Whereas from pi to pi plus alpha, as T1 and D3 are going to conduct, so T1 and D3 are going to get conduct, so therefore then T1 and D3 are going to conduct, so therefore the output voltage is equal to 0 and also the source current is equal to 0. Whereas from pi plus alpha to 2 pi, T2 is a trigger, so therefore T2 and D3 are going to get conduct, so therefore the output voltage is equal to minus of the source voltage, it is negative of the source voltage if you apply the KVL, so therefore the source current is equal to minus I0. Whereas from 2 pi to 2 pi plus alpha or 0 to pi plus alpha, then 0 to alpha, then same thing T2 and D2 are going to conduct, so therefore V naught of T is equal to 0, the output voltage is equal to 0 and the source current is also equal to 0. So this is the things that we are going to analyze. And if you want to find what is the average value of the output voltage, the average value of the output voltage is equal to 1 by 2 pi into 2 times of integration of alpha to pi Vm sin theta d theta. So if you do this simplification, finally we are going to get Vm by pi into 1 plus cos alpha. So Vm by pi into 1 plus cos alpha we are going to get, or simply apply the general principle 2 times of the Vm by 2 pi into cos alpha minus cos beta. Here beta is equal to pi. So finally we are going to get Vm by pi into 1 plus cos alpha is the average value of the output voltage we are going to get. If any freewheeling diode connected across the load, then replace T1 D3 and T2 D2 by freewheeling diode and analyze but graph of V naught of T and IS of T, I naught of T is still same. Suppose if you are going to keep any freewheeling diode across the load, then replace T1 D3 and T2 D2 by freewheeling diode, because in that range this freewheeling diode is going to conduct but not this T1 D3 and T2 D2, because freewheeling diode has less resistance path when compared to these things, so therefore the freewheeling diode is going to get conduct rather than these things. And so because of this, the graph of the V naught of T, and the graph of the IS of T and the graph of the I naught of T will be remain same, but only thing they are going to change the graph of the thyristor current and the graph of the diode current are going to change, but remaining thing are going to remain the same.